Scientists still cannot explain what was discovered beneath Earth's oldest layers, structures that should not exist in that era. And yet deeper anomalies keep appearing, suggesting intelligence predating recorded human history, while artifacts defy modern archaeology, leaving experts questioning everything we assumed about early Earth's unknown past, pulling us closer. Inside a limestone cave overlooking the pale cliffs of southern Iberia, a narrow chamber opens into silence that feels older than memory itself. Stalactites hang like frozen time, and beneath them lie traces of a presence that once walked these shadows with certainty. Here, in sites such as Gibraltar's ancient shelters, fragments of bone and stone tools whisper of a human relative, the Neanderthals. They lived across a vast sweep of Ice Age Eurasia, from the cold forests of Western Europe to the rugged corridors of Central Asia, enduring climates that shifted with little warning. For more than 300,000 years, they adapted to glacial winds, hunted large game, and shaped stone tools with a precision that speaks of experience and intelligence. Their world was not primitive in the way once imagined, but intricate, demanding, and deeply physical. Then, around 40,000 BC, their presence begins to thin. Not abruptly in every region, but unevenly, like a fading signal across a vast landscape. In some caves, their tools are found alongside those of early Homo sapiens, suggesting overlapping occupation. In others, their remains simply stop appearing altogether. The question is not only where they went, but how such a widespread population could diminish across continents within a relatively short span of prehistory. Mainstream explanations point to environmental pressure. The climate during this period was unstable, marked by rapid temperature swings that reshaped ecosystems. Forests retreated, prey migrations shifted, and survival demanded constant adaptation. In such conditions, smaller Neanderthal populations may have struggled to maintain stable genetic diversity. At the same time, early Homo sapiens arrived in Eurasia with broader social networks and more flexible tool traditions, possibly offering subtle advantages in resource competition. Yet the archaeological record does not present a single, clean narrative. In some regions, evidence suggests interaction rather than displacement. Genetic studies reveal that Neanderthals and Homo sapiens interbred, leaving traces of Neanderthal DNA in modern human populations. This complicates the idea of a simple extinction. Did they vanish, or were they gradually absorbed into expanding human communities, their distinct identity dissolving over generations? There are also other layers of inquiry that linger at the edges of scientific consensus. Some researchers have pointed to a dramatic volcanic event, the eruption of the Campanian ignimbrite around 39,000 BC, which may have altered climate patterns across Europe. Ash clouds, reduced sunlight, and ecological disruption could have placed additional strain on already vulnerable populations. Others consider the role of disease transmission between groups meeting for the first time after long isolation, though direct evidence remains elusive. Beyond established frameworks, more speculative interpretations occasionally surface in academic discussion and popular imagination. Some propose that Neanderthals experienced a cognitive disadvantage in symbolic communication, limiting their ability to form expansive social alliances. Others suggest that their disappearance reflects not replacement, but transformation through repeated interbreeding until their distinct lineage became indistinguishable within Homo sapiens. These ideas remain debated, incomplete, and difficult to test against fragmentary remains. Standing in those cave systems today, one is confronted not with absence, but with suggestion. Hand axes still lie embedded in sediment. Hearths mark places where fire once resisted the cold, and faint traces of occupation layers hint at lives that unfolded with intention, care, and adaptation. Nothing here feels accidental, yet nothing fully explains the end of their continuity. So the question persists, carried through layers of stone and time. Did the Neanderthals truly disappear, or did they change form within the unfolding story of humanity, leaving only echoes where once there was a distinct world of their own? The story of the Neanderthals does not end with disappearance alone. It leads, almost quietly, into another discovery. One that emerged not from sweeping landscapes or well-known excavation sites, but from a single remote chamber of stone deep in the Altai Mountains of Siberia. High above the valleys, where cold air settles into the rock and light enters only in narrow angles, lies Denisova Cave. At first glance, it is unremarkable, a shelter shaped by wind, time, and erosion. Yet, within its layered sediments, archaeologists uncovered something unexpected, fragments of a human presence that did not match Neanderthals and did not fully align with modern Homo sapiens. A small finger bone, a few teeth, minute traces of genetic material preserved in conditions that should not have allowed survival across tens of thousands of years. From these fragments emerged an entirely new branch of the human story, the Denisovans. And yet, unlike other ancient human relatives, the Denisovans are not known from complete skeletons or widespread fossil records. They are known primarily through DNA. A genetic signature extracted from a single bone revealed a lineage distinct from both Neanderthals and modern humans, suggesting a population that once spread across parts of Asia in silence, leaving behind very little physical trace. This raises a quiet but persistent question. How could an entire group of humans remain so physically absent from the archaeological record, yet so clearly present in the genetic fabric of those who came after? As research expanded, traces of Denisovan ancestry began to appear in unexpected places. Modern populations in parts of Southeast Asia, Oceania, and even remote mountain regions carry fragments of their DNA. In Tibet, a particular genetic adaptation linked to high-altitude survival, EPAS1, appears to have been inherited from Denisovan ancestry, allowing efficient oxygen processing in thin air. It is a reminder that their legacy did not vanish. It dispersed, embedded within living populations. But the Denisovans themselves remain elusive. Their physical form is still uncertain. From the limited remains, researchers infer robust features, large molars, and a build adapted to harsh environments, yet the full picture is incomplete. Without a broader fossil record, every reconstruction feels provisional, as though observing a shadow cast by something just beyond the reach of discovery. Mainstream interpretations suggest that Denisovans were part of a wider network of archaic human populations spread across Asia, interacting at times with both Neanderthals and early Homo sapiens. Interbreeding events likely occurred, creating genetic overlaps that complicate any simple classification. Rather than isolated branches, the human family tree begins to resemble something more intertwined, more fluid than once imagined. Still, gaps remain. The geographic range of Denisovans is uncertain. Some evidence hints they may have occupied environments stretching far beyond Siberia, perhaps adapting to forests, plateaus, and high-altitude regions across Asia. Yet the scarcity of direct fossils leaves these ideas suspended between possibility and uncertainty. This absence has invited broader speculation. Some researchers consider whether Denisovans were not a single, uniform population, but a collection of related groups spread across vast distances, their differences too subtle to be easily distinguished in the fragmentary record. Others wonder whether future discoveries might reveal entirely new branches hidden within existing classifications, lineages that have not yet been recognized because so little remains of them. There is also the question of why so little physical evidence survives compared to their genetic imprint. Was it a matter of population size, environmental conditions, or simply the accidents of preservation that determine what time chooses to keep? In a landscape as vast and dynamic as ancient Asia, how many other traces might still lie buried, unrecognized beneath layers of earth and stone? Standing again in places like Denisova Cave, the silence feels different from absence. It feels like interruption, something that was once continuous, now only partially visible. Tools rest in sediment layers, but they do not speak clearly. DNA reveals connections, but not daily life. The people themselves remain just out of reach. And so the mystery does not settle. Instead, it expands into deeper uncertainty. Were the Denisovans a single population waiting to be fully uncovered, or a scattered network of ancient humans whose true extent has yet to be revealed by science? The fragments left behind in Denisova Cave do not stand alone in isolation. They sit within a far larger question, one that stretches beyond human ancestry and into the shifting pulse of Earth itself. Because, as the Denisovans faded into genetic traces, something else was unfolding across the planet, written not in bones alone, but in ice, ash, and abruptly changing climates. In the frozen expanse of Greenland, deep ice cores are drilled layer by layer, each one a compressed page of ancient atmosphere. Within them, scientists read a sudden and dramatic shift, a climatic interruption so sharp it feels almost instantaneous in geological terms. Far below, in sediments across North America, Europe, and parts of Asia, similar signatures appear: burned carbon layers, microscopic spheres of glass, a disruption etched into the Earth's surface. This boundary marks what is known as the Younger Dryas period, beginning roughly around 12,900 BC. It represents one of the most abrupt climate reversals in the late Ice Age, a return to near-glacial conditions after a warming trend had already begun to reshape ecosystems. Temperatures dropped rapidly, ice sheets expanded, habitats shifted with little warning. And within this transition, human cultures of the time faced immense pressure. Across parts of North America, archaeological sites associated with early hunter-gatherer groups show sudden changes in settlement patterns. In Eurasia, shifting environments altered migration routes for large game animals, upon which human survival depended. It is a moment in prehistory where adaptation was not gradual, but urgent. Mainstream explanations for the Younger Dryas focus on disruptions in ocean circulation, particularly changes to the Atlantic meridional overturning circulation. The theory suggests that massive influxes of fresh water from melting ice sheets may have slowed or altered ocean currents, triggering rapid cooling across the northern hemisphere. This model is supported by climate simulations and multiple geological records, forming the backbone of scientific understanding. Yet, as with many deep-time events, the record is incomplete, and within that incompleteness, additional hypotheses have emerged. Ideas that attempt to explain the suddenness and global reach of the climate shift. One of the most discussed alternative perspectives is the Younger Dryas impact hypothesis. It proposes that fragments of a disintegrating comet or asteroid may have entered Earth's atmosphere or impacted near or over ice sheets, triggering widespread environmental consequences. According to this view, heat from atmospheric entry or surface impacts could have ignited massive wildfires across continents. Evidence cited includes elevated levels of microscopic carbon particles, nanodiamonds, and unusual concentrations of platinum group elements in sediment layers dating to this period. These markers are debated. Some researchers interpret them as evidence of a cosmic event. Others argue they can be explained by terrestrial processes such as volcanic activity, biomass burning, or sediment reworking. The scientific discussion remains active, with no singular interpretation fully accepted by all experts. But what makes the hypothesis compelling to some is not only the physical evidence, but the timing. The Younger Dryas does not appear as a slow drift into colder conditions. It appears, in many records, as a sharp boundary, a line drawn across climate history. If such an event occurred, what would it have meant for the human populations living through it? Small groups of hunter-gatherers, already adapting to a warming world, would have suddenly faced a reversed climate trajectory. Ice returning to regions that had begun to thaw. Vegetation zones shifting again. Animal migrations breaking familiar patterns. In North America, some researchers point to the disappearance of several large mammal species around this time, including mammoths, mastodons, and saber-toothed predators. The overlap between extinction timelines and climatic disruption has led to further questions about how interconnected these processes may have been. Was it climate alone, or a combination of environmental stress and human presence that reshaped ecosystems so rapidly? In other regions, cultural transitions appear in the archaeological record. Tool technologies change. Settlement evidence becomes sparse in some areas and more concentrated in others. Yet, the narrative is not uniform. Some sites show continuity, suggesting resilience rather than collapse. Others remain ambiguous, their timelines difficult to align precisely with climatic data. This uneven pattern leaves space for interpretation. Could the younger Dryas have acted as a global stress test for early human societies, pushing some to adapt and others to vanish from the record entirely? Or is the apparent suddenness partly an illusion created by gaps in preservation, where time compresses complex transitions into seemingly abrupt shifts? There are also questions that extend beyond earthbound explanations. A minority of researchers have explored the possibility that extraterrestrial factors played a role, not as a confirmed event, but as a framework for interpreting anomalous data clusters. These ideas remain highly speculative and controversial, often challenged for lack of direct impact evidence, such as a definitive crater or unambiguous global ejecta layer. Still, they persist at the edge of discussion, reflecting how unresolved patterns invite broader imagination. Standing in Greenland's ice fields or across the dry plains where ancient lakes once shimmered, it becomes difficult to imagine the speed at which such changes may have unfolded. The Earth does not preserve experience, only traces, and those traces, though measurable, do not always explain themselves. So the younger Dryas remains a boundary in more than climate history. It is a boundary in understanding, a moment where evidence is abundant, but interpretation is still divided. Was it driven entirely by oceanic forces and internal Earth systems? Or did an external trigger accelerate a transition already underway? And beneath that question lies another, quieter one. How many other turning points in Earth's past have we only partially seen, their causes still waiting in the layers of ice, stone, and time to be fully understood? The climate shift of the younger Dryas does not stand alone in Earth's long memory. It becomes part of a broader, more unsettling transformation, one that unfolded as the Ice Age itself drew to a close. Across vast continents once locked beneath glacial cold, something extraordinary began to change. And with it, entire worlds of life disappeared. In the wind-scoured plains of Siberia, frozen ground still preserves the remains of woolly mammoths, their tusks angled toward a sky that no longer exists in the same form. In North America, ancient lake beds once fed by glacial meltwater now lie dry, their sediments holding traces of camels, giant ground sloths, and saber-toothed predators. In South America, cave systems preserve the bones of creatures that once moved through forests now replaced by modern ecosystems. These are not isolated finds. They form a pattern stretching across nearly every continent. Between roughly 50,000 BC and 10,000 BC, a large portion of Earth's megafauna, animals weighing over 44 kilograms, vanished. Mammoths, mastodons, giant kangaroos, cave lions, and glyptodonts disappeared within a relatively narrow window in geological terms. The question is not simply what was lost, but why so many species vanished in what appears, in the fossil record, to be a series of overlapping extinctions. Mainstream scientific interpretations often point toward a combination of climate change and human expansion. As the last ice age ended, temperatures rose, ice sheets retreated, and ecosystems shifted rapidly. Forests replaced tundra in many regions, altering the availability of food sources that megafauna depended upon. At the same time, early human populations expanded into new territories, bringing with them advanced hunting strategies, tools, and in some cases, coordinated group behavior. Evidence from archaeological sites supports human interaction with megafauna. Butchery marks on bones, hunting tools found near remains, and settlement patterns suggest that these animals were not only part of the landscape, but part of human survival strategies. In this view, extinction becomes a complex interaction of environmental stress and increasing predation pressure. Yet the pattern of disappearance is not uniform. Some regions show rapid declines, while others indicate longer periods of coexistence between humans and megafauna. Certain species vanish earlier in some areas than in others, and some survive in isolated pockets long after their continental decline. This uneven rhythm raises questions about whether a single explanation can fully account for the global scale of change. Climate alone does not appear to move with such precision. Human expansion alone does not explain why some large species persisted in areas with significant human presence, while others disappeared in regions with comparatively sparse populations. The overlap of variables suggests a more complex interaction, one that may involve thresholds, points at which environmental and ecological pressures combine in ways that lead to cascading effects. In North America, for example, the disappearance of mammoths and mastodons coincides with the end of the younger Dryas and the onset of warmer, more stable climates. Yet this transition period also includes evidence of sudden ecological disruption. Some researchers have pointed to rapid vegetation shifts that may have altered grazing patterns too quickly for large herbivores to adapt. Others note the fragility of specialized ecosystems that depended on cold-adapted species. In South America, megafauna extinction includes animals unlike those in the northern hemisphere: giant ground sloths that climbed trees, armored glyptodonts resembling massive living tanks, and prehistoric horses that once roamed open plains. Their disappearance raises similar questions. Was it climate stress, human hunting, ecological cascade effects, or a combination of all three? There are also fringe hypotheses that extend beyond traditional frameworks. Some researchers have suggested that abrupt environmental events, such as cosmic impacts or atmospheric disturbances, may have contributed to sudden ecological collapse in certain regions. These ideas are often linked to sediment layers containing unusual concentrations of microscopic particles, carbon spherules, or nanodiamonds. While debated and not widely accepted as definitive evidence of impact events, they continue to be examined as part of ongoing research into abrupt climate and ecological transitions. Other interpretations focus on ecological tipping points. In this view, megafauna extinction was not a single event, but a cascading breakdown. Large herbivores, once removed or reduced in number, would have altered vegetation patterns, which in turn affected predators and soil systems. Such feedback loops could, in theory, accelerate ecological change beyond the capacity of individual species to adapt. There is also the question of human perception. Early humans did not document these changes in written form, leaving only indirect evidence through tools, bones, and environmental traces. Without narrative records, the story must be reconstructed from fragments scattered across time. Each fragment adds detail, but also raises new uncertainty. In caves where megafauna bones accumulate alongside stone tools, it is difficult to separate hunting from scavenging, survival from opportunity. Were these animals actively pursued to extinction, or were humans simply one factor among many in ecosystems already under pressure from shifting climates? The archaeological record does not always provide clear boundaries between cause and consequence. And still, some mysteries persist at the edges. In isolated regions, late surviving populations of megafauna appear in the record long after their presumed extinction elsewhere. These remnants suggest that extinction was not a single horizon event, but a staggered retreat across time and geography. Why did some populations endure while others vanished entirely? As the Ice Age recedes into memory, the landscape itself becomes a kind of archive. Buried footprints in ancient mud, pollen grains preserved in lake sediments, isotopic signatures locked in bones. Together, they form a story that is partially visible, yet never complete. So the disappearance of Ice Age megafauna remains suspended between explanation and uncertainty. Climate change, human expansion, ecological feedbacks, and possible external influences all intersect within the same narrow window of time. But none fully resolves the scale or unevenness of what occurred. And so the question remains open, carried forward like a trace in the sediment of deep time. Did these great creatures fade due to a single driving force? Or were they lost within a convergence of pressures so complex that even now, their final chapter is still only partially written in the ground beneath our feet? The disappearance of Ice Age megafauna leaves behind a world in transition, one where ecosystems unravel and reassemble under pressure, and where survival itself becomes uncertain. But beneath this broader collapse lies another, quieter question. How close did humanity itself come to vanishing alongside them? Far beneath the layered soils of Sumatra, within the rugged highlands of present-day Indonesia, lies the caldera of a sleeping giant. Today it is a vast volcanic lake, Lake Toba, its calm surface masking one of the most powerful eruptions in Earth's recent geological history. The cliffs surrounding it rise like the broken rim of an ancient wound in the planet's surface, shaped by forces difficult to fully comprehend. Roughly around 74,000 BC, this supervolcanic system is believed to have erupted with extraordinary magnitude. Geological evidence suggests an eruption so vast that ash and sulfur aerosols were propelled high into the atmosphere, spreading across continents. Layers of volcanic material have been identified in regions far beyond Southeast Asia, marking a moment of profound planetary disturbance. The mainstream scientific interpretation of this event describes a dramatic volcanic winter. Sunlight would have been partially blocked by atmospheric particles, leading to a significant drop in global temperatures. Some climate models suggest that ecosystems across large portions of the northern hemisphere may have experienced prolonged stress. Vegetation cycles could have been disrupted, food chains strained, environments already sensitive to climatic fluctuation may have become even more fragile. And yet, within this global disturbance, there is a more intimate question, one that concerns not only ecosystems, but human survival itself. Genetic studies of modern human populations have led some researchers to propose that early Homo sapiens may have passed through a population bottleneck during this period. According to this hypothesis, the total number of breeding individuals could have been reduced dramatically, perhaps to a few thousand, or even fewer. This idea is sometimes referred to as the Toba bottleneck hypothesis, though its scale and severity remain widely debated. In this view, humanity did not simply endure a volcanic winter. It came dangerously close to fragmentation, with isolated groups surviving in pockets of habitable land. But where exactly were these refuges? Some models suggest regions of Africa, particularly areas with more stable rainfall patterns, may have provided ecological sanctuaries. Coastal zones, river valleys, and microclimates could have offered temporary resilience against global cooling. In South Asia, too, certain coastal and lowland environments may have buffered climatic extremes, allowing small populations to persist in relative isolation. But the archaeological record from this period is fragmentary. Stone tools remain, but continuous settlement evidence is rare. Fossil preservation is uneven. The result is a timeline that feels discontinuous, as though human presence flickers in and out of visibility across millennia. This absence of clarity has led to further inquiry. Some researchers argue that the genetic bottleneck evidence may reflect not a single catastrophic collapse, but a long-term reduction in population size driven by multiple factors: climate variability, resource scarcity, and ecological competition. In this interpretation, Toba becomes not a singular turning point, but one extreme event among many shaping early human evolution. Still, the sheer scale of the eruption continues to invite deeper questions. Could a single geological event truly reshape the trajectory of an entire species? Or does the genetic signal reflect something more complex? Multiple population contractions layered over time, compressed by the limits of interpretation. Ice core data from Greenland and Antarctica shows changes in atmospheric composition that align broadly with this period, though the exact climatic There are also broader questions about resilience itself. If population numbers were indeed reduced significantly, what does that imply about the fragility of early human existence? Were we always on the edge of disappearance, surviving not through dominance, but through adaptability in the face of repeated environmental shocks? And yet, despite the scale of this event, humanity did not end. It continued. It expanded again. It eventually spread across continents, carrying within its genetic structure faint traces of those ancient survival corridors, signatures of endurance written at the smallest biological level. In this way, the Toba eruption becomes less a story of destruction alone, and more a question of persistence under extreme constraint. But even persistence raises its own uncertainties. If human populations were reduced so dramatically, what cultural, linguistic, or genetic diversity may have been lost during that narrowing of survival? And perhaps most quietly unsettling of all, if humanity once passed so close to collapse, how many other moments in deep time have gone unnoticed? Events that reshaped survival not in a single decisive instant, but through slow pressures that left only faint echoes behind? The lake in Sumatra remains still today, reflecting clouds that drift across a calm surface. But beneath it lies a reminder that stability is often only temporary, and that the boundary between continuity and disappearance may be thinner than it appears. The story of survival through the Toba supereruption leaves behind a subtle but profound implication. Humanity's past was never a single, isolated lineage moving cleanly through time. Instead, as the climate shifted, populations contracted, expanded, and drifted into contact with others they had not seen for tens of thousands of years. And in those encounters, something quietly transformative occurred. To understand this, one must return to the scattered landscapes of Ice Age Eurasia. In the cold forests of Europe, in the limestone caves of the Levant region, and across the high plateaus of Central and South Asia, traces of ancient human presence emerge layer by layer. tools carved from stone, hearths preserved in sediment, bones that carry both familiarity and difference. These are the remnants of multiple human forms sharing the same world, sometimes separated by vast distances, sometimes by only narrow corridors of land. For much of modern history, human evolution was imagined as a straight line, simple, sequential, and exclusive. But genetic research has revealed a more intricate pattern. When the genomes of modern humans were sequenced and compared with ancient remains, something unexpected appeared. Traces of other human groups still embedded within us. Neanderthals, once thought to have vanished completely, left behind fragments of their genetic legacy in most non-African populations today. Denisovans, known primarily from a cave in Siberia, contributed genetic adaptations found in modern populations across parts of Asia and Oceania. These discoveries suggest that early Homo sapiens did not replace other human groups in isolation, but encountered, interacted with, and at times interbred with them. But the deeper mystery is not simply that interbreeding occurred. It is how widespread, how repeated, and how varied these encounters may have been. In the limestone valleys of what is now southeastern Europe, archaeological layers show overlapping tool traditions. In some regions, Neanderthal-style stone technologies appear alongside early Homo sapiens techniques. In others, transitions are gradual, almost blending rather than replacing. These patterns suggest periods of coexistence rather than immediate succession. What did those encounters look like? Were they brief exchanges between distant groups or sustained periods of shared territory? Genetic evidence indicates multiple interbreeding events rather than a single moment of contact. Some of these occurred in the Near East, others likely in Central Asia or elsewhere along migratory routes. The timeline stretches across thousands of years, suggesting repeated crossings of paths between groups that had been separated for extended periods. Yet many questions remain open. The archaeological record rarely preserves direct evidence of social interaction. There are no written accounts, no preserved narratives, only tools, bones, and genetic echoes. From these fragments, researchers attempt to reconstruct not only movement, but contact itself. Mainstream interpretations suggest that interbreeding was likely incidental, occurring when small groups encountered one another in shared environments. As Homo sapiens expanded out of Africa, they entered territories already inhabited by Neanderthals and Denisovans. In these overlapping zones, interactions would have been inevitable, sometimes cooperative, sometimes neutral, and at other times perhaps competitive. But there are alternative interpretations that explore broader possibilities. Some researchers consider whether cultural exchange between these groups may have been more extensive than currently understood. Tool similarities in certain regions raise questions about shared knowledge or parallel development. Could ideas, not just genes, have moved between populations? There is also the question of survival advantage. Certain genetic traits inherited from archaic humans appear to have influenced immunity, skin adaptation, and high-altitude survival in modern populations. This suggests that interbreeding was not only biologically possible, but, in some cases, beneficial. It may have shaped the resilience of early Homo sapiens as they moved into new and challenging environments. Yet even this understanding raises deeper uncertainties. If interbreeding contributed to adaptation, how many other genetic contributions remain unidentified within modern populations? And how many archaic human groups may have existed without leaving recognizable fossil evidence, their existence preserved only in fragments of DNA? Some fringe hypotheses extend this uncertainty further, suggesting that the boundaries between ancient human groups may not have been as rigid as once assumed. Instead of distinct species or subspecies, some propose a broader network of interrelated populations exchanging genes across vast distances over extended periods. In this view, human evolution resembles more a braided stream than a branching tree, constantly splitting, rejoining, and shifting course. Others have speculated about whether certain archaic populations may have persisted longer in isolated regions than currently documented, potentially interacting with Homo sapiens in ways not yet clearly visible in the archaeological record. While these ideas remain highly debated and not widely supported, they reflect the gaps that still exist in our understanding of deep prehistory. Even the concept of identity becomes less stable when viewed through this lens. What does it mean to be a distinct human group in a world where interbreeding was possible across multiple lineages? At what point does genetic blending become transformation rather than replacement? In caves where Neanderthal and Homo sapiens tools appear together, the silence is often the most striking feature. There are no signs of conflict preserved in most cases, no definitive markers of cultural dominance. Instead, there is coexistence written in stone and bone, open to interpretation. Were these shared spaces sites of exchange, competition, or something more complex that defies modern categories? And then there is Denisovan ancestry, still emerging in unexpected genetic findings across modern populations. Their contribution to human diversity is not confined to a single region or time period, but scattered across continents, suggesting encounters that remain largely invisible in the archaeological record. How many more such interactions remain undiscovered, hidden in genetic sequences not yet fully understood? As the narrative of early human evolution expands, it becomes less about isolated origins and more about entanglement. Different human groups moving through shifting climates, responding to environmental pressures, and encountering one another in landscapes shaped by Ice Age extremes, volcanic winters, and ecological upheavals. And yet, despite the growing clarity of genetic science, the lived reality of these encounters remains beyond reach. We can trace ancestry, but not experience. We can identify admixture, but not intention. The emotional, social, and cultural dimensions of these interactions remain largely absent from the record. So the mystery does not resolve into simplicity. Instead, it deepens. Ancient human interbreeding is not a single event to be explained, but a long and intricate process that reshapes how we understand humanity itself. And perhaps the most enduring question is not where these groups came from, but how many more connections between them still lie hidden, waiting in genomes, in unexcavated sites, or in regions of prehistory that have yet to be fully revealed. The story of ancient human interbreeding leaves behind a world where boundaries between human groups are already blurred, where encounters across continents have reshaped what it means to be human. And yet, even after tracing genetic echoes across Eurasia and beyond, there remains another presence, smaller, more isolated, and in some ways even more enigmatic. On a remote island in Southeast Asia, another branch of humanity once lived and, just as quietly, vanished. On the island of Flores, in present-day Indonesia, steep limestone hills rise above dense tropical forest. Beneath them lies a cave known as Liang Bua. It is cool, dim, and layered with sediment that has accumulated over tens of thousands of years. Within this cave, archaeologists uncovered something unexpected: skeletal remains belonging to a small-bodied human population unlike anything previously identified. The remains, dated to around 50,000 BC and possibly earlier, revealed individuals with unusually small stature, approximately 1 meter tall. Their brain size was also significantly reduced compared to modern Homo sapiens. Yet what makes these findings so striking is not only their physical form, but the presence of advanced stone tools found in the same layers. Tools that suggest planning, coordination, and adaptation to a complex environment. This species came to be known as Homo floresiensis, nicknamed the Hobbit After its diminutive size, Homo floresiensis immediately challenged established assumptions about human evolution. It was not simply a primitive ancestor frozen in time. Instead, it appeared relatively recent in the archaeological record, overlapping with modern humans in both time and geography. This overlap introduced a quiet but persistent question. How could such a distinct human form persist into a period already shaped by Homo sapiens' expansion across the region? Mainstream interpretations suggest that Homo floresiensis may represent a long isolated population of early Homo species that underwent insular dwarfism, a biological process in which species evolve smaller body sizes in response to limited resources on islands. Flores, with its complex geography and ecological constraints, would have provided conditions where such adaptations could emerge over long periods of isolation. In this view, Homo floresiensis was not a mystery species outside the human family tree, but a deeply adapted branch shaped by environmental pressures. Their survival on the island may have been supported by hunting small game, scavenging, and utilizing stone tools to exploit a range of ecological niches. Yet the story does not end neatly with adaptation alone. The timing of their disappearance remains uncertain, and the archaeological record leaves behind only fragments. After a certain point, the evidence of their continued presence fades. No clear transition marks their end. No definitive explanation explains their absence. Did they disappear gradually, absorbed into changing ecosystems and environmental pressures? Or did a more abrupt shift occur, leaving only scattered traces behind? Some researchers suggest that volcanic activity in the region may have played a role. Indonesia sits within a highly active tectonic zone, and eruptions throughout prehistory have reshaped landscapes repeatedly. Ash deposits found in nearby regions indicate that environmental disruption was not uncommon. A significant eruption could have altered food sources, water availability, and the fragile ecological balance of island life. Others consider the possibility of competition or interaction with incoming Homo sapiens populations. If modern humans reached Flores during or after the time of Homo floresiensis, encounters between the two groups would have been possible. However, direct evidence of such interaction remains elusive. There are no clearly identified signs of conflict or cultural exchange preserved in the archaeological layers so far uncovered. Still, the absence of evidence is not necessarily evidence of absence. On an island where preservation conditions vary and erosion is constant, entire chapters of prehistory may have been lost. Beyond mainstream explanations, more speculative ideas occasionally surface in discussions of Homo floresiensis. Some researchers have questioned whether the species represents a separate evolutionary branch at all, or whether it could reflect a population of Homo sapiens affected by developmental or environmental conditions that influenced their physical growth. This interpretation remains highly debated, with most evidence supporting a distinct lineage rather than a modern human variant. Other fringe perspectives explore whether Flores and surrounding islands may have hosted multiple, small, isolated human populations whose differences have yet to be fully understood. In such a view, Homo floresiensis might represent one of several now vanished experiments in human adaptation across the fragmented geography of Southeast Asia. There are also broader questions about how isolation shapes intelligence and survival. On an island environment, cognitive demands differ from those on large continental landscapes. Resource management, spatial awareness, and ecological flexibility become critical. Yet the tools associated with Homo floresiensis suggest capabilities that challenge simplistic assumptions about brain size and cognitive capacity. What kind of social structure did they live within? Did they communicate in ways that left no trace in the archaeological record? How did they perceive their own world, surrounded by dense forests, changing sea levels, and volcanic landscapes? And perhaps most strikingly, how did such a small population persist for so long in isolation without leaving a clearer narrative of their presence. As excavation continues in Flores and surrounding regions, new discoveries occasionally reshape the timeline. Stone tools appear in unexpected layers. Sediments shift the estimated dates of habitation. Each new finding adds detail, but also introduces further complexity. In caves like Liangbua, silence is not empty. It is layered. Each layer holds traces of movement, occupation, and absence. Yet none fully explains the final disappearance of those who once lived there. So Homo floresiensis remains suspended between explanation and uncertainty. A population once real, once adapted, once present in a specific and tangible world, now reduced to fragments of bone and stone scattered across time. And the question remains, quietly unresolved. Did they truly vanish from the island entirely, or does their story continue in ways not yet recognized within the deeper patterns of human history? The story of Homo floresiensis leaves behind an island world where human diversity takes unexpected forms, isolated populations adapting in ways that challenge earlier assumptions about evolution, survival, and disappearance. And yet, as we move across the broader map of human prehistory, another mystery emerges, one not confined to islands or caves, but spread across an entire continent at the end of the Ice Age. In the windswept plains of North America, beneath layers of wind-blown sediment and ancient lakebeds, lie finely crafted stone tools that mark a distinct technological tradition. These are the traces of what archaeologists call the Clovis culture. Named after discoveries near Clovis, New Mexico, this tradition is defined by its distinctive fluted projectile points, carefully shaped stone tools designed for hunting large Ice Age animals. Dating to roughly 13,500 BC to 12,800 BC, the Clovis people appear across a vast range of territory in a relatively short span of time. From the southern reaches of what is now the United States to parts of northern Mexico and into various interior regions, their presence is widespread and technologically consistent. For a brief moment in prehistory, their tool tradition seems to define much of human life across North America. And then, just as quickly, it fades. The archaeological record shows a sudden and noticeable decline in Clovis-style tools. Sites that once contained their distinctive points begin to shift toward different, regionally varied technologies. The cultural horizon that once appeared widespread becomes fragmented, replaced by new traditions that are more localized and less uniform. What happened to the Clovis people? Mainstream interpretations often connect their disappearance to environmental change at the end of the last Ice Age. Around this period, the younger Dryas climatic reversal brought abrupt cooling after a warming trend had already begun. Glaciers advanced again in some regions. Ecosystems shifted. Large Ice Age animals, such as mammoths, mastodons, and giant bison, began to decline or disappear. Because Clovis subsistence strategies appear closely linked to big game hunting, particularly of large herbivores, the loss of these animals may have had profound consequences. If the primary food sources disappeared or became scarce, entire lifeways built around them would have needed rapid adaptation. In this view, the Clovis tradition does not vanish in isolation, but transforms under environmental pressure, giving rise to new regional cultures. Yet the transition is not fully clear. Some archaeological sites show rapid cultural change, while others suggest longer periods of continuity. In certain regions, Clovis tools appear alongside evidence of early post-Clovis technologies, raising questions about whether the shift was sudden or gradual, localized or widespread. The uneven nature of the record leaves room for interpretation. There is also the question of population movement. Rather than disappearance, could Clovis groups have migrated into other regions, blending with emerging cultures and losing their distinct technological identity over time? The archaeological signal becomes harder to trace when traditions evolve rather than abruptly end. Then there is the broader ecological context of the younger Dryas boundary itself. Sediment layers from this period in multiple locations contain unusual concentrations of carbon-rich particles, microscopic spherules, and other materials that some researchers associate with large-scale environmental disturbance. These findings have been used to support hypotheses involving abrupt climate shocks, potentially triggered by complex Earth system feedbacks, or, in more debated interpretations, extraterrestrial impacts. The idea of a sudden environmental catastrophe affecting human populations and megafauna, at the same time, has led some researchers to reconsider the speed and scale of cultural transitions during this period. If ecosystems were disrupted rapidly, even highly adapted human groups like the Clovis people may have faced cascading challenges: food scarcity, migration pressures, and increased competition. However, these interpretations remain actively debated. Many archaeologists emphasize the importance of gradual ecological change and human adaptation over time rather than a single catastrophic event. In this view, the Clovis disappearance reflects a complex interplay of environmental variability, demographic shifts, and cultural innovation. Still, the abruptness in the archaeological record continues to raise questions. Why does such a widespread and technologically consistent tradition appear to decline within a relatively narrow window of time? And why does its disappearance align so closely with one of the most dramatic climate fluctuations of the late Ice Age? Beyond established frameworks, some alternative perspectives suggest that the Clovis tradition may represent not a single population, but a network of interconnected groups sharing a technological style across vast distances. In this interpretation, the disappearance of Clovis could reflect the breakdown of long-distance connections rather than the loss of a single people. As climate conditions shifted, those networks may have fragmented, leading to localized cultural divergence. Others propose that the archaeological record may be incomplete in ways not yet fully understood. Sites may remain undiscovered, buried beneath sediment, or erased by geological processes over thousands of years. In such a vast landscape, absence of evidence does not always equate to evidence of absence. There are also broader questions about identity itself. What defines a culture in deep prehistory? Is it a shared technology, a genetic population, a way of life, or a combination of all three? When Clovis tools disappear from the record, does that indicate the end of a people, or simply the transformation of their way of living into something archaeologists no longer recognize as the same tradition? In some regions, post-Clovis technologies show continuity in hunting practices, but changes in tool design. This suggests adaptation rather than total replacement. The people may have remained, while their material expression evolved in response to new conditions. If so, the disappearance of Clovis becomes less a vanishing point and more a transition zone, where identity shifts gradually, leaving only faint traces of its former form. And yet, the pattern still feels incomplete. Across North America, there are still gaps in the timeline, regions where evidence is sparse or absent, and periods where cultural sequences are difficult to reconstruct with precision. Each new discovery has the potential to reshape the understanding of this transition, but also to complicate it further. So the Clovis disappearance remains suspended in uncertainty. Not a clean ending, but a fading presence across a changing landscape, one shaped by climate instability, ecological transformation, and human adaptability. And the question lingers, quietly persistent. Did the Clovis people truly vanish, or did they simply dissolve into the next chapter of human history, their identity transformed so gradually that only their tools remain to hint at what once was? The fading traces of the Clovis tradition leave behind a continent already in motion, cultures shifting, environments transforming, and older certainties dissolving into uncertainty. Yet beneath this transition lies an even deeper question. one that stretches beyond a single culture or moment in time. Because before Clovis, before the established archaeological horizons of North America, there is something more fundamental still being pieced together: the story of the first humans to reach the Americas. In the far north, where Alaska meets the edge of the Bering Strait, the landscape narrows into a quiet threshold between continents. Today, cold waters separate Asia and North America. But during the last ice age, sea levels were lower, and a vast exposed region known as Beringia connected Siberia to Alaska. It was not a bridge in the modern sense, but a broad, shifting expanse of tundra and steppe, cold, open, and rich with migrating herds of Ice Age animals. It is here, in this transitional world of ice and land, that the earliest movements into the Americas are believed to have begun. Mainstream archaeological understanding suggests that humans entered the Americas sometime after 20,000 BC, with more widely accepted occupation evidence appearing closer to 16,000 BC and later. These early groups are thought to have followed animal migrations, gradually moving southward through corridors that opened between retreating ice sheets. Over generations, they spread across vast territories, eventually reaching both North and South America. Sites such as Monteverde in present-day Chile, dated to around 14,500 BC, provide strong evidence of early human presence far south of the initial entry points. This suggests a remarkably rapid expansion across the continents once entry was established. But the question that continues to shape research is not only when humans arrived, but how many times and by what routes. For decades, the dominant model emphasized a single migration route through an ice-free corridor that opened between massive glacial formations in North America. According to this interpretation, early populations moved southward through this corridor as it became passable, eventually dispersing across the continent. However, newer evidence has expanded this picture. Coastal migration models propose that early humans may have traveled along the Pacific coastline, using waterways, marine resources, and coastal refuges that have since been submerged by rising sea levels. If this is correct, much of the earliest evidence of human presence may now lie underwater, inaccessible beneath the continental shelf. This raises a profound possibility: that the archaeological record we see today may represent only a fraction of the original pathways into the Americas. Stone tools, hearth remains, and ancient habitation sites continue to emerge across both North and South America, but they do not always align neatly with a single migration narrative. Some sites appear earlier than expected. Others challenge assumptions about technological development and adaptation. Each discovery adds detail, but also introduces new uncertainty. And so the deeper question emerges: was the peopling of the Americas a single wave, or a series of movements across thousands of years? Genetic studies have added another layer to this complexity. Modern indigenous populations of the Americas share ancestral connections that trace back to populations in northeastern Asia. But the timing, structure, and diversity of these ancestral groups suggests that the process may not have been linear. Instead, it may reflect a long period of population mixing, isolation, and movement within Beringia before expansion into the broader continents. Some researchers describe Beringia not merely as a route, but as a refugial region, an environment where populations may have remained isolated for thousands of years during glacial maximums. In this view, the ancestors of the first Americans were not simply passing through, but living, adapting, and evolving in a cold, dynamic landscape before dispersing outward when environmental conditions changed. Yet even this framework leaves open questions. Why do some early archaeological sites appear so far south, seemingly early in the timeline of continental expansion? How quickly did humans adapt to such dramatically different ecosystems, from Arctic tundra to tropical forests, from high-altitude plateaus to coastal plains? There are also sites that continue to generate debate within the scientific community. Certain locations in North and South America have produced evidence that some researchers interpret as suggesting earlier than expected human presence, though these interpretations are often contested. The difficulty lies in distinguishing human-made artifacts from naturally occurring formations, especially in deeply ancient contexts where preservation is inconsistent. Beyond mainstream interpretations, some fringe hypotheses propose even more complex scenarios. These include the possibility of multiple migration waves occurring at different times, involving distinct populations with separate technological traditions. Others speculate about coastal routes so early that their evidence may now be entirely submerged, erased by rising sea levels at the end of the Ice Age. There are also broader questions about the adaptability required for such journeys. The environments encountered by early migrants into the Americas were among the most diverse on Earth. Glacial tundra, dense forests, arid plains, mountain ranges, and vast river systems. Survival in such conditions would have required not only mobility, but deep ecological understanding and flexibility in subsistence strategies. What did these early groups experience as they moved through unfamiliar landscapes? How did they interpret the new ecosystems they encountered, filled with unfamiliar animals, plants, and seasonal cycles? These are questions that archaeology can approach, but never fully answer. And as sea levels rose at the end of the Ice Age, many coastal regions that may have supported early human movement were submerged. Entire chapters of prehistory may now lie beneath the ocean, inaccessible except through indirect evidence. What remains on land may only be fragments of a much larger story. The emergence of later cultural traditions, including Clovis, adds further complexity to the narrative. Rather than a simple beginning point, Clovis now appears within a broader continuum of earlier and possibly overlapping populations. This suggests that the first humans to reach the Americas may have been part of a much longer and more intricate process of settlement and adaptation than previously understood. In this way, the story of the first Americans is not a single moment of arrival, but a gradual unfolding across time and landscape. A movement shaped by climate shifts, ecological opportunity, and human resilience. Yet even as models grow more detailed, certainty remains elusive. So the question persists, quiet but unresolved. Were the first humans to reach the Americas part of one unified migration, or do they represent multiple still hidden pathways into a continent whose earliest chapters remain only partially written beneath layers of time, water, and ice? The journey into the first human migrations across the Americas leaves behind a broader, more intimate question, one that does not belong to a single region or time period, but to the entire unfolding of humanity itself. Because beneath every migration, every adaptation, and every disappearance lies a quieter mystery still. How human intelligence itself evolved, and why it took the shape it did. In the layered sediments of ancient caves, from the limestone chambers of Europe to the volcanic shelters of Southeast Asia, there are traces not only of human presence, but of changing behavior over time. Stone tools become more refined. Fire is controlled with increasing consistency. Symbolic markings begin to appear. These are subtle shifts, but they suggest something profound unfolding beneath the surface of survival. Human intelligence did not emerge suddenly. It appears gradually, unevenly, across different regions and timelines. In some places, technological complexity increases, while in others it remains relatively stable for thousands of years. This uneven progression raises questions about what drives cognitive change. Is it purely biological evolution, or does environment play a shaping role in how intelligence develops and expresses itself? Mainstream scientific understanding places the evolution of modern human cognition within the broader timeline of Homo sapiens, emerging roughly 300,000 BC in Africa. Over time, anatomical changes in the brain, particularly in regions associated with language, planning, and social cognition, are believed to have supported increasingly complex forms of thought. These changes are reflected in archaeological evidence, more sophisticated tools, evidence of long-distance trade, and the emergence of symbolic expression. Cave paintings found in regions such as present-day France and Palestine, dating back tens of thousands of years, suggest that early humans were capable of abstract representation. Handprints, animal figures, and geometric patterns appear on stone surfaces deep within cave systems, often placed in locations that would have required deliberate effort to reach. Why were these images created in such hidden spaces? What meaning did they hold for those who made them? Yet intelligence is not visible in fossils alone. It must be inferred from behavior, and behavior is preserved only in fragments. A sharpened stone, a carved bone, a hearth. These are indirect signals of thought processes we cannot directly observe. And so the story of human intelligence remains, in many ways, an interpretation built from partial evidence. One of the central questions in this field is why human intelligence developed to such a degree compared to other species. Many animals demonstrate problem-solving abilities, social complexity, and communication systems. Yet humans developed cumulative culture, knowledge that builds across generations, expanding rather than resetting with each cycle of life. Some researchers suggest that social complexity played a critical role. As early human groups grew larger and more interconnected, the ability to understand relationships, predict behavior, and cooperate may have driven cognitive expansion. In this view, intelligence is not just a tool for interacting with the environment, but for navigating social worlds. Others emphasize environmental variability. Rapid climate fluctuations during the Ice Age may have required flexible thinking and adaptive strategies. In unstable environments, survival may have depended less on instinct and more on innovation. The ability to plan, imagine alternative outcomes, and transmit knowledge could have provided a decisive advantage. But even these explanations leave gaps. Neanderthals, Denisovans, and other archaic human groups also demonstrated forms of intelligence. They created tools, used fire, and in some cases, buried their dead. Yet their cognitive trajectories did not lead to the same global expansion as Homo sapiens. Why? Was it a matter of incremental advantage, or something more subtle in communication, cooperation, or symbolic thinking? Genetic studies reveal small but significant differences in brain development pathways between modern humans and archaic relatives. However, the relationship between genetics and cognition is not fully understood. Intelligence does not map neatly onto single genes or simple biological markers. It emerges from complex interactions between biology, environment, and culture. And culture itself may have played a role in accelerating cognitive development. Once symbolic communication emerged, whether through gesture, sound, or early language systems, it may have created feedback loops of increasing complexity. Ideas could be shared, refined, and transmitted. Knowledge became cumulative rather than isolated. Still, the origin of symbolic thought remains one of the most difficult transitions to define clearly in the archaeological record. At what point does a mark on stone become communication? At what point does repetition become language? These thresholds are not easily defined, yet they mark a profound shift in human experience. Some fringe perspectives suggest that human intelligence may have been influenced not only by gradual evolution, but by sudden leaps tied to environmental or genetic events that are not yet fully understood. These ideas remain outside mainstream consensus, but they reflect ongoing uncertainty about how incremental changes accumulate into something as complex as modern cognition. There are also questions about the uneven development of intelligence-related technologies across different regions. In some parts of the world, advanced tool traditions appear relatively early, while in others, similar levels of complexity emerge much later. Does this reflect independent development, cultural exchange, or simply gaps in the archaeological record? And beyond tools and artifacts lies a deeper, more elusive question. What did early humans experience internally? How did they perceive time, memory, and self-awareness? Intelligence is not only external behavior, but internal awareness, something that leaves no direct trace in stone or sediment. As we trace the evolution of human intelligence across hundreds of thousands of years, the pattern that emerges is not linear. It is uneven, adaptive, and deeply responsive to changing conditions. Moments of rapid innovation are followed by long periods of stability. Ideas appear, evolve, and sometimes disappear without clear explanation. And yet, through all this uncertainty, one fact remains constant. Intelligence continues to expand in ways that are still unfolding today. So the question does not settle. It widens. Was human intelligence the inevitable result of evolutionary pressure, or a rare convergence of conditions that could have unfolded differently under another set of circumstances? And as we look back through the fragmented record of our origins, how many stages of cognitive development remain hidden, waiting in the silent spaces between artifacts, genetics, and the limits of interpretation? The evolution of human intelligence leaves behind a silent but powerful implication. At some point, thought became shareable, not only experienced internally, but transmitted between individuals in structured, meaningful ways. And from that threshold emerges another question, one that is even more elusive in the archaeological record. How did modern human language begin? In the quiet echo chambers of ancient landscapes, language itself leaves no direct fossil. There are no preserved sentences in stone, no recordings in sediment. Yet scattered across archaeological sites are indirect signs that point toward its emergence. Carefully shaped tools that require instruction. Coordinated hunting strategies that imply communication. Symbolic markings etched into bone and rock, suggesting that meaning was being assigned, shared, and refined. Some of the earliest hints come from deep within prehistoric caves, where markings appear not as random scratches, but as repeated patterns. Handprints pressed against stone walls, sequences of lines arranged in deliberate forms. In places such as southern Europe and parts of Africa, these markings date back tens of thousands of years. They do not speak in words, yet they seem to suggest an intention to communicate beyond immediate survival. Modern linguistic science places the origin of fully developed spoken language somewhere within the timeline of Homo sapiens, likely emerging gradually rather than in a single moment. Anatomical studies of the human vocal tract show adaptations that allow for a wide range of sounds, changes in the larynx, tongue control, and neural coordination. These physical traits suggest that humans became biologically capable of complex speech over a long evolutionary period. But capability does not explain emergence. The question remains, when did structured language first take shape, and what form did it initially take? One mainstream theory proposes that language evolved from increasingly complex forms of social communication. Early humans likely used gestures, facial expressions, and vocalizations to coordinate group behavior. Over time, these signals may have become more abstract, allowing sounds to represent objects, actions, and eventually ideas. In this view, language did not appear suddenly, but as a gradual refinement of existing communication systems. Another perspective emphasizes the role of survival pressure. In environments where cooperation was essential, such as hunting large Ice Age animals or navigating shifting climates, more precise communication may have offered a significant advantage. The ability to share information about danger, resources, or social relationships could have directly influenced survival outcomes. Yet even these explanations leave something unresolved. Language is not only functional, it is also symbolic. It allows humans to speak about things that are not present, not immediate, and sometimes not real. It enables imagination, storytelling, and the transmission of abstract ideas across generations. How did such a system emerge from purely practical communication? In archaeological layers associated with early Homo sapiens, evidence of symbolic thought appears alongside technological development. Beads made from shells, pigments such as ochre, and carved objects suggest that meaning was being attached to material objects. These may represent some of the earliest forms of symbolic expression that could have been linked to proto-language systems. Genetic research has also entered the discussion. Certain genes associated with speech and language processing, such as FOXP2, show variations in modern humans that differ from those found in archaic human species. However, these genetic differences alone do not fully explain the emergence of language. They provide capacity, but not structure. And structure is the most elusive part. Some researchers suggest that language may have emerged relatively quickly in evolutionary terms, possibly within a narrow window of time. This idea is often associated with the concept of cognitive leap theories, where changes in brain connectivity may have enabled recursive thinking, the ability to embed thoughts within thoughts, forming complex sentences and abstract concepts. If this occurred, it would represent a profound shift in how information could be processed and shared. Others argue for a slower, more incremental development, stretching across hundreds of thousands of years. In this interpretation, early forms of language may have been highly context-dependent, lacking grammar as we understand it today. Over time, these systems may have grown in complexity, eventually reaching the structured languages observed in later human societies. There are also alternative perspectives that remain outside mainstream consensus. Some propose that language may have multiple origins, emerging independently in different populations before converging through interaction and migration. Others suggest that early language systems may have been far more diverse than currently assumed, with many experimental forms existing before some became dominant and others disappeared without leaving clear traces. One of the enduring mysteries is why language is so universal among modern humans. Across continents and cultures, all known human societies possess structured language systems. This suggests either a single origin or a deeply embedded cognitive capacity shared by all Homo sapiens. But the path to that universality remains unclear. In certain archaeological contexts, it is difficult to distinguish between symbolic communication and fully developed language. A carved symbol may represent a sound, an idea, or an entirely different form of meaning. Without direct evidence, interpretation becomes layered and uncertain. And yet, language is not only a tool of communication, it shapes thought itself. The ability to name, to categorize, and to describe may have fundamentally altered how humans perceive reality. Did language emerge as a reflection of thought, or did it actively reshape thought into new forms? As we move through the record of human evolution, from tools to art, from migration to symbolic expression, the emergence of language appears not as a single event, but as a gradual deepening of complexity. A shift that is difficult to locate in time, yet impossible to separate from everything that followed. And still, questions remain suspended in that silence before speech became fully structured. What did early communication sound like? How close were the first meaningful words to gesture, to emotion, to instinct? And perhaps most intriguingly, how much of that earliest language has been lost entirely, leaving no trace except the world it helped create? The emergence of language leaves behind a world increasingly shaped by communication, symbolism, and shared meaning. Yet even as we trace its development across continents and millennia, there remain pockets of humanity whose place in that story is still uncertain. Figures who appear late in the timeline of human evolution, yet seem strangely disconnected from the patterns expected of their era. In the limestone karst landscapes of southern China, where mist rises through forested valleys and cave mouths open like dark windows into the past, archaeologists uncovered remains that would challenge conventional timelines. Inside these caves, particularly in regions such as Yunnan, human fossils were discovered that did not fit neatly into the expected narrative of modern human variation. These remains became known as the Red Deer Cave People, named after evidence suggesting their diet may have included large game such as deer species found in the region. Dating estimates place these individuals at roughly 14,000 to 11,000 BC, a relatively recent period in human prehistory. This alone is striking. By this time, Homo sapiens had already spread widely across Asia, developed complex tools, and in many regions, established increasingly sophisticated cultural traditions. Yet the physical characteristics of the Red Deer Cave remains appear unexpectedly archaic. The skulls exhibit a combination of traits that do not align easily with typical modern human morphology. Certain features appear robust, with broader facial structures and characteristics that some researchers describe as reminiscent of earlier human forms. At the same time, they are clearly not identical to any known archaic human species. They seem to occupy a space between categories, anomalous, difficult to classify, and therefore difficult to fully interpret. This raises an immediate question. Who were they? And how did they persist into such a late period of human history? Mainstream interpretations tend to approach the Red Deer Cave people cautiously. One explanation suggests that they represent a localized population of early modern humans who retained certain ancestral physical traits due to regional isolation. In this view, their differences are not evidence of a separate species, but rather variation within Homo sapiens that persisted longer in certain environments. Another possibility considers the effects of genetic diversity and population structure in prehistoric Asia. The region is vast, ecologically varied, and historically home to multiple human populations, including Homo sapiens, Denisovans, and potentially other yet unidentified groups. In such a complex environment, physical variation could have been more pronounced than in later, more interconnected populations. Yet the archaeological record from the caves where these remains were found offers only partial clarity. Stone tools and animal bones appear alongside the human fossils, but the cultural context is not fully developed or easily linked to broader technological traditions of the same period. This absence of clear cultural alignment adds another layer of uncertainty. Were these individuals part of a larger, isolated community whose material culture simply has not been fully preserved? Or do they represent a transitional population, existing at the edges of genetic and cultural convergence? Some researchers have suggested that the Red Deer Cave people may reflect a late surviving population of archaic humans, persisting in isolated regions of East Asia longer than previously assumed. While this idea is not widely accepted, it reflects the broader uncertainty surrounding human diversity during the late Pleistocene. The possibility that multiple human lineages coexisted in different regions for extended periods remains an active area of scientific exploration. At the same time, environmental factors may have played a significant role. The period in which these individuals lived was one of ecological transition. The end of the Ice Age brought shifting climates, changing vegetation patterns, and altered animal distributions. In such conditions, isolated groups could have experienced unique evolutionary pressures, leading to physical adaptations that differ from neighboring populations. But physical form is only part of the question. Behavior leaves fewer traces, yet it is equally important in understanding identity. What kind of lives did the Red Deer Cave people lead? How did they communicate, organize socially, or interpret the rapidly changing world around them? The caves themselves offer only fragments. Hearth remnants suggest the use of fire. Animal bones indicate subsistence practices, but without a fully developed cultural framework, interpretation remains limited. There are no preserved texts, no symbolic systems that can be clearly identified, and no definitive markers of social structure. And so, like many discoveries at the edges of human prehistory, the Red Deer Cave remains exist in a space between clarity and ambiguity. Beyond mainstream interpretations, more speculative ideas occasionally emerge in discussions of such anomalous remains. Some propose that East Asia during the late Pleistocene may have hosted a greater diversity of human populations than currently recognized, with small, isolated groups surviving in ecological refuges. Others suggest that the boundaries between different human lineages may have been more fluid, with overlapping traits reflecting long-term interaction and genetic exchange. There are also broader questions about how archaeological classification itself shapes interpretation. Human remains are categorized based on comparative anatomy, but what happens when a population does not fit cleanly into existing categories? Does classification reflect biological reality, or does it impose structure on a record that is inherently incomplete? In caves where these remains were found, time feels layered rather than linear. Sediments accumulate slowly, preserving traces of occupation that may span generations or centuries. Yet within those layers, continuity is difficult to reconstruct with precision. Each discovery adds detail, but also raises new uncertainties about who these people were and how they relate to the broader human story. And then there is the larger context. By 14,000 to 11,000 BC, much of the world was already connected through expanding human populations. Trade networks in some regions were beginning to form. Symbolic expression was becoming more widespread. Language, as explored earlier, was already deeply embedded in human life. Against this backdrop, the Red Deer Cave people appear as an unexpected presence, neither clearly separated from their time nor fully integrated into its broader patterns. So the mystery remains open. Were the Red Deer Cave people a distinct and isolated population, a regional variation of modern humans, or something else entirely that has yet to be fully understood within the framework of human evolution? And as new discoveries continue to emerge from the caves of East Asia, one question quietly persists beneath the surface of the record. How many other human stories from the late Ice Age still lie hidden, waiting to reshape what we think we know about our own recent past? The anomalies of the Red Deer Cave people leave behind a final impression that human prehistory is not a single clean progression, but a mosaic of overlapping populations, environments, and adaptations. And as these fragments accumulate across time, they converge toward one of the most profound turning points in Earth's recent past, the disappearance of a vast portion of life at the end of the Ice Age. Across the northern hemisphere, the landscape at the close of the Pleistocene was undergoing a transformation so extensive that it reshaped entire ecosystems. In the frozen soils of Siberia, mammoth steppe grasses once stretched for thousands of kilometers. In North America, vast herds of large herbivores moved across open plains, while predators followed in cycles that had persisted for millennia. In South America, giant ground sloths, armored glyptodonts, and prehistoric horses formed complex ecological networks that no longer exist today. And then, within a relatively narrow window between roughly 15,000 BC and 8,000 BC, many of these species disappeared. This event, often referred to as the late Pleistocene extinction wave, saw the loss of a significant proportion of Earth's large mammals. Mammoths, mastodons, saber-toothed cats, cave lions, dire wolves, giant beavers, and many others vanished across multiple continents. The scale of this loss was not isolated or regional. It was global in reach, yet uneven in timing and pattern. What makes this extinction wave so compelling is not only its magnitude, but its complexity. The archaeological and paleontological records do not present a single, unified cause. Instead, they reveal overlapping pressures, shifting timelines, and regional variations that resist simple explanation. Mainstream scientific interpretations often point toward a combination of climate change and human expansion. As the Ice Age came to an end, global temperatures rose, ice sheets retreated, and ecosystems reorganized at a rapid pace. Habitats that had supported cold-adapted megafauna for thousands of years began to disappear or transform. Forests replaced grasslands in some regions. Seasonal patterns shifted. Water availability changed. At the same time, human populations were expanding into new territories. With increasingly sophisticated tools and hunting strategies, early Homo sapiens interacted with megafauna across multiple continents. Evidence of hunting and butchery appears in some archaeological sites, suggesting that human activity contributed to the pressure on already vulnerable species. Yet the timing and distribution of extinctions do not always align neatly with either climate change or human presence alone. Some species disappeared before significant human arrival in certain regions. Others survived for thousands of years alongside human populations before vanishing. This uneven pattern raises deeper questions about how multiple forces may have interacted. Climate models suggest that the end of the Pleistocene was not a simple warming trend, but a period of rapid fluctuation. The younger Dryas event, for example, introduced a sudden return to colder conditions around 12,900 BC, temporarily reversing earlier warming. Such abrupt changes could have placed additional stress on ecosystems already in transition. Vegetation shifts would have altered grazing patterns. Migratory routes may have changed or collapsed entirely. Species dependent on specific ecological conditions may have found themselves unable to adapt quickly enough. In this view, extinction becomes a cascading process rather than a single trigger event. But even this explanation leaves gaps. Why did some large animals survive while others disappeared? In certain regions, isolated populations of megafauna persisted long after their counterparts vanished elsewhere. Mammoths survived on remote Arctic islands thousands of years after mainland populations were gone. This staggered pattern suggests that extinction was not uniform, but fragmented across geography and time. Some researchers propose that ecological tipping points may have played a critical role. In this framework, ecosystems can absorb gradual change until a threshold is reached, after which rapid collapse occurs. The removal of a single species, or a combination of environmental stresses, could potentially trigger a chain reaction affecting multiple interconnected species. Human activity may also have played a role in these tipping dynamics. Even relatively small human populations, when introduced into ecosystems with species unaccustomed to human predation, could have had disproportionate effects. However, the extent of this influence remains a subject of ongoing debate. Beyond established models, alternative hypotheses occasionally emerge. Some researchers have explored the possibility of extraterrestrial impacts or atmospheric disturbances contributing to abrupt environmental changes at the end of the Ice Age. These ideas are often linked to sediment layers containing unusual concentrations of microscopic materials such as carbon spherules or nanodiamonds. While controversial and not widely accepted as definitive evidence of impact events, they continue to be examined as part of broader investigations into abrupt climate disruptions. Other perspectives focus on the role of disease, suggesting that pathogens introduced through human migration or environmental change could have affected vulnerable animal populations. However, direct evidence for widespread disease-driven extinction in the late Pleistocene remains limited. Still, the most striking feature of this extinction wave is its simultaneity across multiple continents. From North America to Eurasia, from South America to Australia, large-bodied animals disappeared within overlapping timeframes. The coordination of this loss across such vast distances remains difficult to fully reconcile with any single explanation. And so, the late Pleistocene extinction wave stands not as a simple endpoint, but as a convergence of uncertainties. Climate instability, ecological fragility, human expansion, and possibly other yet unidentified factors all appear to intersect within this critical window of time. In many ways, this extinction marks more than the disappearance of species. It marks a transformation of global ecosystems into the world we recognize today. Forests replaced grasslands. Smaller, more adaptable species became dominant. Human presence became increasingly central to ecological systems across continents. Yet despite the scale of what was lost, the record remains incomplete. Many species are known only from fragmentary remains. Entire ecosystems must be inferred from scattered evidence. And in some regions, the timing of extinction remains uncertain, blurred by gaps in preservation. So the question remains unresolved. Was the late Pleistocene extinction wave the result of a single dominant force acting across the globe, or the outcome of multiple interacting pressures that reached a critical threshold simultaneously across different environments? And perhaps more quietly, how many other moments in Earth's deep past resemble this one? Events where complexity hides behind the appearance of sudden disappearance, waiting for future discoveries to reveal what is still unseen beneath the layers of time. The late Pleistocene extinction wave leaves behind a world reshaped, emptier in some ways, but also newly open. Large animals fade from the landscape, ecosystems reorganize, and human populations begin to expand more visibly into the spaces once dominated by Ice Age megafauna. Out of that transformation emerges a deeper question, one that no single archaeological site can fully contain. Why did only humans go on to build complex civilization? The question does not begin in a city, but in silence. In the dry bed of an ancient river valley, once flowing through Mesopotamia, layers of sediment preserve the slow accumulation of human presence. Here, over thousands of years, small settlements grow into villages, and villages into early urban centers. Clay tablets appear. Irrigation channels reshape the land. Organized labor, symbolic writing, and structured governance begin to take form. Yet this is only one place among many where human societies begin to intensify their complexity. Similar patterns appear independently across the world. In the river valleys of the Nile, along the Indus Basin, in the valleys of ancient China, and later in the highlands of the Andes, human groups transition from mobile or semi-mobile lifeways into increasingly structured societies. Cities emerge. Writing systems develop. Astronomy, mathematics, and law take shape in diverse cultural contexts. And yet, despite this global spread of Homo sapiens, only one species on Earth follows this trajectory. No other known species develops cumulative civilization, systems of writing, agriculture, urban infrastructure, and long-distance governance that build across generations rather than resetting with each cycle of life. Why? Mainstream scientific explanations begin with biology and cognition. Humans possess unusually large and energy-intensive brains relative to body size. This supports abstract reasoning, long-term planning, and symbolic thought. Combined with opposable thumbs, upright locomotion, and fine motor control, these traits allow for complex tool-making and environmental manipulation. But intelligence alone does not explain civilization. Many species demonstrate problem-solving abilities. Corvids use tools. Dolphins communicate with intricate vocal patterns. Elephants exhibit long-term memory and social complexity. Yet none of these lineages develop cumulative technological civilizations. Their knowledge, however sophisticated, does not appear to build indefinitely across generations in the way human knowledge does. This leads researchers to consider another factor: Cumulative culture. Humans uniquely transmit knowledge in a way that not only preserves information, but expands it. Each generation inherits not just survival strategies, but increasingly complex systems of language, technology, and social organization. This accumulation creates a feedback loop, where knowledge itself becomes a driver of further complexity. Language plays a central role in this process. As explored earlier in this series, human language allows for abstraction, recursion, and the transmission of ideas beyond immediate experience. It enables coordination between large groups, the preservation of memory across generations, and the creation of shared symbolic systems. With language, humans can describe things that do not yet exist. But even this does not fully resolve the question. Environmental theories suggest that Earth's variability may have played a key role. During the Ice Age and its aftermath, climates shifted repeatedly. Habitats expanded and contracted. Resources moved across landscapes. In such conditions, adaptability becomes essential. Groups that could share information effectively about changing environments may have had survival advantages. Some researchers propose that civilization emerges not from stability, but from instability. In constantly changing environments, flexible thinking, cooperation, and innovation may become essential survival traits. Over time, these traits could accumulate into the foundations of agriculture, settlement, and eventually urban complexity. Yet even this framework has limits. Environmental change has affected many species across Earth's history. Yet none outside Homo sapiens appear to have crossed the threshold into cumulative civilization. This has led to more speculative interpretations, ideas that sit at the edges of scientific discourse. Some suggest that the development of human civilization may have depended on a rare convergence of factors: cognitive capacity, environmental variability, social structure, and anatomical flexibility occurring simultaneously within a single lineage. In this view, civilization is not inevitable, but contingent, a rare outcome of overlapping conditions that could easily have unfolded differently. Others explore the possibility that early Homo sapiens possessed unique social pressures that encouraged cooperation at unusually large scales. Unlike many species, humans form alliances between groups, not just within them. Trade networks in prehistory suggest that even early societies exchanged materials across long distances. Obsidian, shells, and pigments move across landscapes, indicating early forms of economic and symbolic connection. But even here, questions remain. Why did this capacity for cooperation intensify rather than dissipate over time? Many species cooperate, but few expand cooperation into systems of governance that persist across generations. The archaeological record shows that early human societies experimented with different forms of organization long before stable civilizations emerged. Settlements appear, dissolve, and reappear in different forms. Agriculture is independently developed in multiple regions around the world between roughly 10,000 BC and 3000 BC. This suggests not a single origin of civilization, but multiple converging pathways. Yet only Homo sapiens crosses the threshold into sustained, large-scale civilization. Some fringe hypotheses suggest that unknown factors may still be missing from current models. These include the possibility that cognitive evolution in humans reached a threshold not shared by other species, or that social learning mechanisms in humans are uniquely capable of exponential complexity growth. Others speculate about lost periods of experimentation in prehistory, civilizations or proto-civilizations that may have existed but left little trace due to environmental destruction or sea level rise at the end of the Ice Age. Rising seas following the last glacial maximum submerged vast coastal regions around the world. If early complex societies existed in these areas, their traces may now lie beneath oceans, inaccessible to traditional archaeology. While there is no confirmed evidence of fully developed lost civilizations from this period, the possibility continues to be explored in theoretical discussions. Still, even without invoking lost histories, the question remains profound. Why does civilization, as a cumulative and self-expanding system, appear only in one species on Earth? Is it the result of a rare biological configuration, a unique combination of environmental pressures, or an emergent property of intelligence once it reaches a certain threshold? Or is civilization not a single outcome at all, but a fragile process, one that requires continuous reinforcement, cooperation, and transmission across time to sustain itself? And if that is true, then another question quietly follows. How many other forms of intelligence, adaptation, or social complexity might exist in nature that simply do not leave behind the kind of trace we recognize as civilization? As the layers of human prehistory accumulate, from extinction waves to migrations, from language to intelligence itself, the emergence of civilization does not appear as an endpoint, but as one expression of a much larger mystery. And perhaps the most unsettling question remains unanswered. Was human civilization an inevitable outcome of evolution, or a rare convergence of conditions that, under different circumstances, might never have happened at all? The emergence of human civilization leaves behind a world defined by expansion, ideas spreading across continents, technologies accumulating across generations, and societies forming increasingly complex networks of cooperation. Yet long before the first cities rose, before agriculture reshaped landscapes, and even before the earliest global cultural connections took form, there was another moment of extraordinary human movement, one that pushed the boundaries of what was geographically and cognitively possible at the time. Far to the southeast of the ancient continents of Africa and Eurasia lies a vast landmass surrounded by deep ocean waters. Australia, isolated by seas for tens of thousands of years, preserves landscapes that appear almost unchanged in their ancient form. Arid deserts stretching into the horizon, eucalyptus forests shaped by fire, and coastlines carved by wind and tide. Within this environment lies evidence of one of the most remarkable chapters in human prehistory, the arrival of the first humans to this continent. Archaeological findings across Australia suggest human presence dating back at least 65,000 BC, and possibly earlier, depending on ongoing interpretations of sediment layers and artifact contexts. Sites such as Madjed Baby in northern Australia have produced stone tools, pigment fragments, and signs of controlled fire use that point to early and sustained human occupation. But what makes this migration so extraordinary is not only its timing, but its scale of achievement. To reach Australia from the nearest parts of Southeast Asia, early humans would have had to cross multiple stretches of open water. Even during periods of lower sea levels, when land masses were more closely connected, there were still significant marine barriers requiring intentional or accidental seafaring capabilities. This implies not only physical capability, but also cognitive and technological adaptation that allowed early humans to navigate unknown environments beyond sight of land. How did such a journey begin? Mainstream archaeological interpretation suggests that modern humans moved through Southeast Asia in a gradual expansion, eventually reaching the Sahul landmass, a combined Ice Age continent that included present-day Australia, Tasmania, and New Guinea when sea levels were lower. Even so, reaching Sahul required crossing at least several water gaps, meaning early humans likely used some form of watercraft, whether simple rafts, floating logs, or more structured vessels. This suggests a level of planning and risk-taking behavior that challenges earlier assumptions about prehistoric mobility. It is not merely migration across land, but movement into uncertainty across water, a different kind of frontier entirely. Once in Australia, early human populations rapidly spread across diverse environments. They adapted to deserts, rainforests, and coastal regions, developing cultural systems that reflected deep ecological knowledge. Rock art traditions, some of which may date back tens of thousands of years, offer glimpses into symbolic thought, storytelling, and environmental understanding. These are not static traces, but evolving expressions of human presence in a new and complex land. Yet even with growing archaeological evidence, many aspects of this migration remain uncertain. One of the central questions concerns timing and routes. Did humans reach Australia in a single migration wave, or through multiple movements over thousands of years? Some models suggest coastal dispersal routes along Southeast Asia and island chains, while others propose more complex patterns of movement involving island hopping and intermittent settlement across fragmented landscapes. Another question concerns the technology used. No definitive ancient boats have been preserved from this period, leaving only indirect evidence. The absence of physical watercraft forces researchers to reconstruct possibility from geography and survival logic rather than direct artifacts. And then there is the broader question of motivation. What drove early humans to cross into such isolated and distant environments? Was it population pressure, resource scarcity, environmental change, or simply exploratory behavior embedded within human adaptability? The answer may lie in a combination of these factors, but the archaeological record cannot fully reconstruct intention. Some researchers suggest that early human expansion into Australia reflects a level of cognitive sophistication already present tens of thousands of years earlier than previously assumed. The ability to plan long-distance movement, adapt to unfamiliar ecosystems, and sustain populations across diverse environments implies a high degree of behavioral flexibility. Others emphasize environmental opportunity. Lower sea levels during glacial periods exposed more land in Southeast Asia, creating stepping stone islands that may have facilitated gradual movement. In this view, Australia was not reached in a single bold crossing, but through incremental movement across shifting landscapes. Yet even this explanation leaves gaps. Certain islands between Southeast Asia and Australia show limited evidence of early human occupation, raising questions about whether some regions were used as transient points rather than permanent settlements. If so, many traces of these journeys may have been lost to rising sea levels after the end of the Ice Age, when vast coastal areas were submerged. This possibility introduces a deeper uncertainty. How much of early maritime activity has disappeared beneath the ocean? If early humans were capable of crossing water gaps into Australia, it is reasonable to consider that similar movements may have occurred along now submerged coastlines throughout the region. Beyond mainstream models, more speculative ideas occasionally emerge. Some propose that early seafaring abilities may have developed earlier and more rapidly than currently recognized, potentially appearing independently in multiple regions. Others suggest that cognitive and navigational skills required for such journeys may reflect an underappreciated level of technological experimentation in prehistory, even in societies without permanent settlements. There are also broader questions about perception and memory. How did early humans conceptualize the ocean? Was it seen as a barrier, a pathway, or something entirely different within their worldview? Without written records, such interpretations remain inaccessible, reconstructed only through material remains and environmental inference. In Australia itself, the arrival of humans marks the beginning of long-term ecological transformation. Evidence suggests the use of fire as a land management tool, reshaping vegetation patterns and influencing biodiversity over thousands of years. Some researchers argue that human activity contributed to the extinction of certain megafauna species unique to the continent, though climate factors are also considered part of the equation. These interactions highlight a broader pattern seen across human prehistory. Wherever Homo sapiens arrived, environments began to change in response. Yet Australia presents a particularly early and isolated example of this phenomenon, making it a critical case study in understanding human ecological impact. Still, many uncertainties remain. If humans reached Australia by at least 65,000 BC, this places their maritime capabilities among the earliest known evidence of long-distance seafaring behavior in human history. But the archaeological record does not clearly show the developmental stages leading up to this achievement. Where did this knowledge originate? Was it developed gradually, or did it emerge through earlier, now-lost episodes of experimentation and movement across water? And perhaps the most enduring question of all, how many other journeys like this, silent, unrecorded, and transformative, have disappeared into the deep past, leaving only fragments of stone, ash, and memory scattered across a continent that was once entirely new to human eyes? The story of early human arrival in Australia closes a chapter of extraordinary expansion, one in which Homo sapiens pushed across oceans, adapted to new continents, and reshaped entire ecosystems. Yet even as modern humans spread across the globe, the deeper human family tree still holds branches that are far less understood. Some appear briefly in the archaeological record, only to fade again into uncertainty. Among the most enigmatic of these is a species discovered not in open landscapes, but deep within the hidden stone corridors of South Africa, Homo naledi. Far beneath the rolling hills of the cradle of humankind, northwest of present-day Johannesburg, lies a vast underground cave system known as Rising Star. Its limestone passages are narrow, twisting, and in places so restricted that access requires crawling through tight rock channels. Within these isolated chambers, illuminated only by artificial light today, researchers uncovered something unexpected. Hundreds of fossilized remains belonging to a previously unknown human relative. The remains of Homo naledi were not scattered randomly. They were found in deliberate, concentrated deposits deep inside the cave system, far from natural light and difficult to access even with modern equipment. The chambers where they were discovered are not easily reached by chance or natural processes. This immediately raised questions about how the remains came to rest in such locations. Dating studies have placed Homo naledi relatively recently in the timeline of human evolution, possibly between 335,000 and 236,000 BC, though interpretations continue to be refined as new evidence emerges. This timing is significant. It places Homo naledi in a world where early Homo sapiens were already emerging in Africa, and where multiple human species may have coexisted across overlapping regions. Yet Homo naledi does not fit neatly into expectations of either archaic or modern human form. Their anatomy presents a striking combination of traits. The skull is relatively small, suggesting a brain size closer to earlier hominin species. Yet other features, such as aspects of their hands and feet, suggest abilities for both climbing and upright walking. Their hands, in particular, show a blend of dexterity and curvature that may have supported tool use alongside climbing behavior. This mixture of traits challenges simple linear models of human evolution, and yet the most puzzling aspect is not only who they were, but where and how they appear in the archaeological record. The deep cave chambers where Homo naledi remains were found are not naturally illuminated or easily accessible. Some passages are extremely narrow, requiring careful navigation even for trained researchers. The presence of multiple individuals in these remote chambers has led to one of the most debated questions in paleoanthropology. How did they get there? Mainstream interpretations remain cautious. One possibility is that the cave system acted as a natural trap over time, with individuals accidentally falling into deep chambers or becoming separated from groups. Over long periods, remains could have accumulated through repeated, unintentional entry into dangerous areas of the cave system. However, this explanation does not fully resolve all aspects of the findings. The concentration and placement of remains in certain chambers have led some researchers to consider alternative possibilities, including deliberate deposition. This idea suggests that Homo naledi may have engaged in some form of behavioral practice involving the placement of bodies in deep cave spaces. If true, this would carry profound implications. It would suggest symbolic or ritual behavior in a human relative with a brain significantly smaller than that of Homo sapiens. It would challenge long-standing assumptions that complex mortuary practices are directly tied to larger brain size or modern cognitive architecture. Yet this interpretation remains debated. Critics point out that evidence for intentional burial behavior in Homo naledi is not conclusive, and that natural geological processes cannot be entirely ruled out. The cave system itself is complex, and sediment shifts over thousands of years may obscure original deposition patterns. Still, the question lingers in the background of all interpretations. Why were these remains found so deep within a system so difficult to access? Beyond the question of deposition lies another, even broader mystery. Why does Homo naledi appear to exist so late in the timeline of human evolution, alongside other more cognitively advanced human species? If the proposed dates are correct, Homo naledi may have lived at the same time as early Homo sapiens in Africa. This raises the possibility that multiple human species coexisted in the same regions, perhaps interacting indirectly or occupying different ecological niches. The idea that human evolution was not a clean replacement sequence, but a branching and overlapping network, becomes increasingly difficult to dismiss. In this context, Homo naledi becomes part of a larger pattern seen across human prehistory. Neanderthals in Europe, Denisovans in Asia, Homo floresiensis in Southeast Asia, all suggest a world in which multiple human forms existed simultaneously, each adapted to different environments, each with their own evolutionary trajectory. But Homo naledi stands out because of its apparent temporal placement and its unusual archaeological context. Some researchers have suggested that the species may represent a long-surviving relic population of an earlier hominin lineage, persisting in isolated regions of southern Africa long after other branches had evolved or disappeared. In this view, Homo naledi would not be an anomaly, but a surviving fragment of a much older evolutionary landscape. Others propose that their physical traits may reflect a unique evolutionary path shaped by environmental pressures in southern Africa, potentially leading to a mosaic of ancient and derived features. This interpretation emphasizes evolutionary diversity rather than linear progression. There are also more speculative ideas, though they remain outside mainstream scientific consensus. Some have suggested that the behavior associated with the cave deposits, if intentional, could imply cognitive capacities not yet fully understood within small-brained hominin species. Others question whether the archaeological record is complete enough to rule out alternative explanations for both behavior and chronology. However, the scientific community continues to approach these interpretations with caution, emphasizing the need for further evidence before drawing definitive conclusions. What remains undisputed is the significance of the discovery itself. Homo naledi adds complexity to the human story, challenging assumptions about evolution, cognition, and behavior. It expands the range of what is considered possible within the human lineage. Yet many questions remain unresolved. How did Homo naledi fit into the broader ecological and social landscape of their time? Did they interact with other human species, or remain isolated within specific regions? And perhaps most intriguingly, what does their presence in such deep and inaccessible cave chambers reveal about behavior, intention, and the limits of our understanding of early human cognition? As the layers of human prehistory continue to unfold, from migration to extinction, from language to intelligence itself, Homo naledi remains suspended in uncertainty. A presence both ancient and unexpectedly recent, familiar in some ways, unfamiliar in others. And so the question remains open, echoing through the silent chambers of Rising Star. What other human forms, behaviors, or worlds might still be hidden beneath the surface of the fossil record, waiting to reshape everything we think we know about our own origins? The deep cave chambers of Rising Star, where Homo naledi once left behind traces of an uncertain presence, close another chapter in the long and intricate story of human evolution. Yet as we move forward through time, the focus shifts from hidden underground passages to something far more familiar, something that walks beside us even today. In the quiet transition between wilderness and human settlement, where Ice Age landscapes began to soften into post-glacial environments, another relationship was forming. One that would reshape survival, mobility, and emotional life itself. It did not begin in a single place. There is no clear map marking its origin. Instead, it emerges gradually across scattered archaeological sites from Europe, Asia, and the Arctic fringe. The first domestication of dogs. In ancient sediment layers across Eurasia, archaeologists have uncovered remains of canids that appear neither fully wolf nor fully dog. Their skulls show subtle changes in jaw structure. Their teeth suggest dietary shifts. Their bodies reflect a transition, one that does not align cleanly with wild predation or fully domestic companionship. These remains, dated broadly between 30,000 BC and 15,000 BC depending on interpretation, hint at a long and gradual transformation. But what makes this transition so compelling is not only biological change, it is behavioral proximity. Some of the earliest potential evidence of human-canid relationships comes from burial sites where humans and dogs appear together. In certain cases, dogs are found placed carefully alongside human remains, suggesting a relationship that extended beyond utility. In other contexts, canid remains show signs of healed injuries, implying long-term survival that would have been unlikely without human support. Yet the question remains, how did this relationship begin? Mainstream scientific interpretations suggest that domestication was not a single event, but a gradual coevolutionary process. Wolves that were less fearful of humans may have been drawn to the edges of early human settlements, scavenging leftover food. Over generations, those that tolerated human presence more effectively would have had survival advantages. In turn, humans may have benefited from the presence of alert animals capable of detecting danger, tracking prey, and assisting in hunting. In this view, domestication is not a moment of control, but a slow alignment of two species adapting to each other's presence. Still, even this explanation leaves gaps in understanding. One of the central mysteries is timing. Genetic studies suggest that dogs diverged from wolf populations tens of thousands of years ago, but the exact point of domestication remains uncertain. Different studies propose different regions and timeframes, ranging from Europe to Central Asia to Siberia. Some findings even suggest multiple domestication events that may have merged over time into the lineage of modern dogs. This raises a deeper question. Was there a single origin of domestication, or several parallel beginnings that converged later in history? Archaeological evidence adds further complexity. In certain Paleolithic sites, canid remains show morphological changes that suggest early domestication, yet these changes do not always appear consistently across regions or time periods. Some populations seem to retain wild characteristics, while others show clear signs of human association. This uneven pattern suggests that domestication may not have been a uniform process, but a mosaic of localized interactions. And then there is behavior. Unlike many domesticated animals, dogs exhibit a unique capacity for interpreting human gestures and emotional cues. This ability is not easily explained by simple training or environmental conditioning. It suggests a deep evolutionary alignment between species, one that extends beyond basic survival interactions. How did such an alignment emerge in a world without language as we understand it today? Some researchers propose that early humans and wolves may have engaged in mutualistic relationships long before formal domestication. Hunting cooperation could have provided advantages for both species. Wolves tracking prey may have followed human groups, while humans may have benefited from the wolves' sensory abilities. Over time, this cooperation could have become increasingly structured, eventually leading to genetic and behavioral divergence from wild wolf populations. Yet even this model does not fully explain the emotional depth observed in the human-dog bond. Archaeological sites where dogs are buried alongside humans, sometimes with signs of care or ritual placement, suggest a relationship that may have extended beyond practicality. Was this companionship intentional from the beginning, or did emotional attachment emerge gradually through shared survival experiences? Beyond mainstream interpretations, more speculative ideas occasionally appear in discussions of domestication origins. Some suggest that early human societies may have recognized behavioral differences within wolf populations more consciously than previously assumed, selectively engaging with individuals that exhibited social tolerance. Others propose that environmental pressures during the late Ice Age may have accelerated the convergence of human and canid lifeways in unexpected ways. There are also broader questions about cognition. The domestication of dogs may represent one of the earliest examples of cross-species communication shaping evolutionary trajectories. If humans and wolves were capable of forming cooperative bonds tens of thousands of years ago, what does that imply about the flexibility of cognition in both species? And what does it suggest about the nature of domestication itself? Rather than a one-sided process of control, domestication may instead represent a shared evolutionary pathway, one in which both species undergo changes in response to prolonged interaction. Dogs became more attuned to human social cues, while humans may have developed new forms of environmental awareness shaped by canine cooperation. In some archaeological contexts, the presence of early dogs coincides with changes in human settlement patterns. Groups with canid companions may have had advantages in mobility, hunting efficiency, or territory awareness. These advantages, accumulated over generations, could have influenced broader patterns of human expansion and survival. Yet, despite growing evidence, many aspects remain uncertain. Where exactly did domestication begin? Was it a single region or multiple independent events? How did early humans interpret the behavior of wolves before domestication fully emerged? And perhaps most intriguingly, at what point did cooperation transform into companionship? Because unlike other domesticated animals, dogs occupy a unique space in human life. They are not only tools of survival, but participants in social and emotional worlds. This depth of connection suggests a history far more complex than simple utility. As we trace the long arc from Ice Age landscapes to early human societies, the domestication of dogs appears not as a discrete event, but as a slow, unfolding relationship, one that bridges species boundaries in ways still not fully understood. And so the mystery remains open, lingering in the quiet spaces between archaeology and behavior. Did humans truly domesticate dogs? Or did two species, shaped by shared environments and survival pressures, gradually learn to understand each other in ways that still defy complete explanation today? The long history of human companionship with dogs leaves behind a subtle but profound implication: that intelligence alone does not define humanity. Cooperation, emotion, memory, and shared understanding all seem to play a role in shaping what humans became. Yet beneath all of these traits lies a deeper question, one that has followed this entire journey from the earliest migrations to the rise of civilization itself. What is human consciousness? The question does not begin in laboratories or written philosophy. It begins in perception itself. In the stillness of ancient landscapes, long before writing systems recorded thought, consciousness already existed as lived experience. A hunter standing at the edge of a vast Ice Age plain, watching shifting herds in the distance. A fire burning inside a cave, casting moving shadows across stone walls. A hand pressing pigment against rock, leaving behind a mark that outlives its maker. These moments do not describe consciousness. They are consciousness, expressed through interaction with the world. Yet despite its immediacy, consciousness leaves no fossil. No bone reveals awareness. No tool captures subjective experience. And so, unlike migration patterns, extinction events, or even language development, consciousness remains one of the few subjects in human history that cannot be directly reconstructed from material evidence. Modern neuroscience approaches consciousness through the structure and activity of the brain. Billions of neurons communicate through electrical and chemical signals, forming networks that process sensory input, memory, emotion, and decision-making. Functional imaging studies reveal patterns of activity associated with perception, attention, and self-awareness. And yet, even with this knowledge, a fundamental gap remains. We can observe the brain in action. We can measure signals, map regions, and correlate activity with behavior. But the subjective experience, the feeling of being aware, of existing as an observer within thought, remains outside direct scientific measurement. This is often described as the hard problem of consciousness. Why and how physical processes in the brain produce subjective experience at all. From an evolutionary perspective, consciousness appears to have developed gradually. Early organisms respond to stimuli without awareness. More complex animals exhibit learning, memory, and decision-making. In mammals, particularly primates, social complexity correlates with increased cognitive capacity. Humans represent an extreme continuation of this trajectory, with advanced abstraction, self-reflection, and symbolic thought. But at what point does processing become awareness? Some researchers suggest that consciousness is not a single feature, but a spectrum. Under this model, different species may possess different levels or forms of awareness, shaped by ecological and neurological demands. In this view, human consciousness is not a binary distinction, but an intensification of processes that exist throughout the animal kingdom. Yet this explanation, while useful, does not fully resolve the mystery of subjective experience. Why does perception feel like something from the inside? Throughout history, human cultures have attempted to understand consciousness through philosophy, spirituality, and mythology. Ancient traditions often describe consciousness as separate from the body, or as something that transcends physical existence. These interpretations vary widely, but they share a common recognition. Awareness feels fundamentally distinct from the material world it observes. Even within early human societies, evidence of symbolic thought suggests an awareness of inner experience. Burial practices, artistic expression, and ritual behavior imply that early humans recognized concepts of identity, memory, and perhaps even continuity beyond physical life. These behaviors appear tens of thousands of years ago, long before formal philosophical systems emerged. In modern scientific discourse, consciousness is often linked to specific brain structures, particularly the cerebral cortex and its complex network of connections. Yet even this does not fully explain why integrated neural activity should produce subjective awareness rather than silent computation. Some theories propose that consciousness arises from the integration of information across the brain. Others suggest it may emerge from specific patterns of complexity or feedback loops within neural networks. There are even hypotheses that treat consciousness as a fundamental property of the universe, similar to space or time rather than something produced solely by biological systems. None of these models fully resolves the question. and so consciousness remains both familiar and deeply mysterious. It is the lens through which all human experience is filtered, yet it cannot be observed directly from outside. Every scientific attempt to study it must rely on behavior, language, or neural activity, indirect expressions of something inherently internal. This creates a unique paradox. Consciousness is the only phenomenon in the universe that we know exists because we are it. As human evolution progressed, from early tool use to language, from migration to civilization, consciousness appears to have expanded in complexity. The ability to reflect on one's own thoughts, to imagine alternate realities, to construct abstract systems of meaning, all suggest a form of awareness that extends beyond immediate sensory experience. But whether this expansion represents a true increase in consciousness or simply a refinement of expression remains unclear. Some speculative perspectives propose that consciousness may not be fully contained within the brain, but instead emerges from interactions between the brain and broader environmental or informational systems. Others suggest that what is perceived as individual consciousness may be part of a larger, interconnected framework of awareness. These ideas remain outside mainstream scientific consensus, but they reflect ongoing uncertainty about the boundaries of subjective experience. Even within established science, new questions continue to arise. Artificial intelligence research, for example, challenges assumptions about whether complex information processing alone could produce something resembling awareness. If machines can simulate aspects of human cognition, does that imply any form of consciousness, or merely its imitation? And if consciousness can emerge in artificial systems, what does that reveal about its underlying nature? Across the entire arc of human history, from prehistoric caves to modern cities, consciousness remains the constant background presence. It is the observer of extinction events, the architect of civilization, the source of language, and the driver of exploration. Yet it is also the least understood element of all. Even as science maps the brain with increasing precision, the inner experience of awareness remains beyond direct explanation. The question is not only how consciousness works, but why it exists in the form it does at all. And so the mystery persists. Is consciousness an emergent property of complexity, a biological adaptation for survival, or something more fundamental that predates life itself? And as research continues to probe the boundaries of neuroscience and philosophy, one final question remains suspended in the silence behind all perception. What is it that is truly observing this moment of awareness, and will it ever be fully known? The exploration of consciousness leaves us suspended at the edge of inner experience itself, aware of awareness, yet unable to fully explain it from the outside. And as the investigation moves deeper into what it means to be human, another question quietly emerges from the biological record, written not in thought, but in skin. Why did humans lose most of their body hair? It is a transformation so complete that it often goes unnoticed in daily life. Compared to our closest primate relatives, chimpanzees, gorillas, orangutans, the human body appears strikingly bare. Scattered patches of hair remain, but the dense covering that once defined early mammalian ancestry has largely vanished. And yet, this absence is not a loss in the evolutionary sense. It is a change that demands explanation. To understand it, we begin not in laboratories or modern cities, but in ancient environments where early hominins moved through shifting landscapes of heat, shadow, and survival pressure. Millions of years ago, early human ancestors were covered in thick body hair, much like other primates. This hair provided insulation, protection, and camouflage within forested environments. But as climatic conditions changed across Africa, forests gave way to more open savanna landscapes. Heat became a constant presence. Shade became scarce. And survival began to depend not on insulation, but on the ability to regulate internal temperature efficiently. In this environmental shift lies one of the leading mainstream explanations: thermoregulation. As early hominins became more active during daylight hours, walking longer distances, tracking food sources, and engaging in persistence hunting strategies, the need to dissipate heat effectively became increasingly important. Dense body hair, while protective, can trap heat and reduce cooling efficiency. In this model, individuals with slightly reduced body hair may have had a survival advantage in hotter environments, allowing them to remain active for longer periods without overheating. Sweating plays a central role in this explanation. Humans possess an unusually high density of eccrine sweat glands compared to most mammals. This system allows for efficient cooling through evaporation. However, for sweating to be effective, skin must be exposed. Dense fur would trap moisture and reduce cooling efficiency. Over time, natural selection may have favored reduced body hair in combination with increased sweating capacity. But this explanation, while compelling, does not fully resolve the mystery. Because body hair is not merely functional, it is also biological memory. Hair patterns are influenced by complex genetic pathways that regulate development long before birth. The reduction of body hair in humans is not a simple switch, but a gradual evolutionary adjustment affecting multiple systems over millions of years. And yet, even with this complexity, the question remains: why did this change occur so extensively in humans, but not in other primates facing similar environmental pressures? Some researchers suggest that the answer may lie not only in heat, but in parasites. In warm environments, dense body hair can provide habitat for ticks, lice, and other parasitic organisms. A reduction in body hair may have reduced parasite load, decreasing the risk of disease transmission and improving overall health. In this interpretation, hair loss is not only about temperature regulation, but about hygiene at an evolutionary scale. Still, this explanation also leaves gaps. Many mammals in similar environments retain thick fur and have developed alternative parasite control strategies. Why would humans diverge so dramatically? Another widely discussed hypothesis involves aquatic or semi-aquatic adaptation theories. Although not universally accepted, this perspective suggests that early humans may have spent significant time near or in water environments, where reduced body hair could have provided advantages such as faster drying, improved swimming efficiency, or reduced drag. In this view, hair reduction would be a byproduct of an ecological shift toward water-rich habitats. However, fossil and archaeological evidence for sustained aquatic adaptation remains limited, and this hypothesis remains debated within scientific circles. A third explanation focuses on social and sexual selection. In this model, body hair reduction may have been influenced not only by survival pressures, but by mate selection preferences. Visible skin allows for more direct perception of health indicators such as coloration, injury, or physiological condition. Over time, individuals with less body hair may have been perceived as more attractive or healthier, influencing reproductive success and gradually shaping population traits. This introduces a different kind of evolutionary force, not environmental necessity, but social perception. Yet even this idea raises further questions. Social selection requires existing cognitive and social complexity. If preferences influenced body hair evolution, then those preferences themselves must have already been established. This creates a recursive loop in which biology and behavior shape each other over time, and so the mystery deepens rather than resolves. Because unlike many evolutionary traits, body hair reduction in humans is extreme in scale. It is not a minor adjustment, but a near-total transformation of a characteristic that is deeply conserved across mammals. Such a dramatic shift suggests a combination of multiple overlapping pressures rather than a single cause. Thermoregulation, parasite reduction, sexual selection, and environmental adaptation may all have contributed in varying degrees. but how these factors interacted, and in what sequence, remains uncertain. The fossil record offers limited clarity. Hair itself does not fossilize easily, leaving scientists to infer its presence or absence from indirect evidence such as skin impressions, genetic markers, and comparisons with related species. Ancient DNA studies have identified genetic variations associated with hair density, pigmentation, and follicle development, suggesting that changes occurred gradually over hundreds of thousands of years. Yet genetics alone cannot reconstruct the lived experience of this transformation. What did early humans look like during intermediate stages of this change? Were there populations with partial reduction of body hair? Did environmental variation produce regional differences in hair density across early human groups? These questions remain open, as the archaeological record preserves only fragments of the story. In some speculative interpretations, researchers have even considered whether body hair reduction might have played a role in broader aspects of human development, such as social bonding. Reduced hair may have increased the importance of touch, physical closeness, and visual communication. Skin-to-skin contact could have taken on new significance in social and parental interactions, potentially influencing emotional development and group cohesion. These ideas remain exploratory, but they highlight an important point. Biological change is rarely isolated from behavioral consequence. As humans became less fur-covered, they also became more visually expressive. Facial cues, gestures, and body language may have gained prominence as communication tools. The visible skin of the human body became a canvas for emotion, injury, health, and identity. And yet, despite these possibilities, no single explanation fully accounts for the scale and consistency of the transformation across the human species. Even across diverse environments, tropical, temperate, and high altitude, humans share a relatively uniform reduction in body hair compared to other primates. This suggests that the change occurred early in our evolutionary history, before global dispersal, and became fixed within the Homo lineage. But why this trait, and not others, became so deeply embedded remains unresolved. Because evolution does not always produce symmetrical answers. It produces outcomes shaped by overlapping pressures, chance events, and historical contingencies that are difficult to reconstruct with precision. And so the absence of body hair becomes something more than a biological trait. It becomes a record of adaptation without a fully recoverable narrative. As we step back from the microscopic details of genes, climate, and behavior, a broader question emerges. Was the loss of body hair a necessary adaptation that enabled human survival in changing environments, or an incidental outcome of multiple pressures converging in a way that could have easily unfolded differently under alternate conditions? And perhaps more quietly, what other aspects of human biology, so familiar today that they seem inevitable, are in fact the result of rare and fragile pathways in our deep evolutionary past? Pathways that could have led to an entirely different form of humanity altogether? The story of human evolution often moves through invisible shifts, changes in climate, anatomy, behavior, and perception that accumulate slowly across vast stretches of time. The loss of body hair marks one such transformation, subtle in appearance, yet profound in implication. And as we follow these threads further into the late Ice Age world, another pattern emerges, one that reveals not change within humans alone, but the final echoes of an ancient world fading unevenly across the planet. In the frozen reaches of the northern hemisphere, where tundra once stretched uninterrupted across continents, massive herds of mammoths moved through landscapes shaped by wind, ice, and grasslands, known as the Mammoth Steppe. These were not isolated animals in a single region, but part of a vast ecological system spanning Europe, Asia, and North America. For hundreds of thousands of years, mammoths, along with other Ice Age megafauna, thrived in these cold, dry environments. And yet, While most populations vanished around the end of the last ice age, a few isolated groups survived far longer than expected, clinging to existence on remote islands long after their mainland relatives had disappeared. One of the most remarkable examples comes from Wrangel Island, located in the Arctic Ocean north of Siberia. Here, a population of woolly mammoths survived until roughly 2000 BC, thousands of years after mammoths had disappeared from mainland Eurasia and North America. In geological terms, this is an extraordinary lag. A species once widespread across continents persisted in a small, isolated refuge, while the world around it had already moved into a new ecological era. Even earlier, another isolated population survived on St. Paul Island in the Bering Sea, with evidence suggesting mammoths may have persisted there until around 6000 BC, or slightly later, depending on interpretations. These remnants of a once global species existed in ecological pockets long after their broader extinction. The question is not simply that they survived, but why they survived where others did not. Mainstream scientific explanations begin with geography. As the Ice Age ended and sea levels rose, vast land bridges disappeared beneath the ocean. Populations of mammoths became increasingly fragmented, cut off from the larger gene pools that once supported their genetic diversity. Isolated on islands, these populations were no longer part of the vast migratory systems that had sustained them for millennia. On Wrangel Island, in particular, mammoths were cut off from mainland populations roughly 10,000 BC. From that point onward, they existed in a confined environment, gradually shrinking in population size and genetic diversity over time. This isolation likely led to inbreeding, reduced fertility, and increased vulnerability to environmental fluctuations. In this model, extinction was not sudden. It was a slow narrowing of possibility. Yet, isolation alone does not fully explain the timing or the duration of survival. Why did mammoths persist for thousands of years in these limited environments when similar mainland populations had already disappeared? Climate change remains a central factor. As global temperatures rose, the mammoth steppe began to transform. Grasslands gave way to forests and wetlands in many regions, reducing the availability of the dry, cold-adapted vegetation that mammoths depended on. On islands, however, local climatic conditions sometimes remained relatively stable for longer periods. Microclimates could have provided temporary refuges, delaying ecological collapse. But even these refuges were fragile. As populations shrink, ecological systems become more sensitive to small changes. A single harsh winter, a shift in vegetation, or a disruption in food supply can have disproportionate effects on survival. On isolated islands, mammoths would have had limited ability to migrate in response to changing conditions. And yet, they persisted. This persistence raises deeper questions about resilience in isolated ecosystems. What allows a species to survive long after its global decline has begun? Is it purely environmental stability, or does behavioral adaptation play a role even in species already under ecological pressure? Some researchers suggest that island populations may have undergone evolutionary changes that allowed them to survive longer than their mainland counterparts. Wrangel Island mammoths, for example, appear to have exhibited genetic mutations affecting growth, reproduction, and metabolism. These changes may reflect adaptation to limited resources and small population sizes. Smaller body size, delayed maturation, and altered reproductive cycles have all been proposed as potential responses to island conditions. In this view, mammoths were not simply surviving, they were changing. Yet even adaptation has limits. As ecosystems continue to shift, even highly adapted populations can reach thresholds beyond which survival is no longer possible. The final extinction of Wrangel Island mammoths around 2000 BC coincides with a period of environmental change and increasing human presence in surrounding regions. However, the exact role of human activity in their extinction remains debated. Some interpretations suggest that human hunting may have contributed to pressure on already vulnerable populations. Others argue that environmental factors alone, such as vegetation changes, freshwater availability, or climatic variability, may have been sufficient to bring about their eventual disappearance. What is striking, however, is the timing. While human civilizations were already developing in parts of the world, mammoths were still alive in remote Arctic environments. This overlap compresses the sense of deep time. The mammoth, often imagined as belonging to a distant prehistoric past, was in fact still present during the early stages of human civilization. Stone tools, early writing systems, and emerging cities existed in a world where mammoths still walked on isolated Arctic islands. This temporal overlap challenges simplified narratives of extinction. It suggests not a single ending, but a staggered retreat across geography and time. Beyond mainstream explanations, some speculative ideas have emerged regarding island survival dynamics. One perspective considers whether mammoths may have occupied ecological niches that were less immediately affected by broader environmental changes. In such scenarios, survival is not about resistance to change, but about delayed exposure to it. Another idea explores the possibility that island ecosystems can function as time capsules, preserving ancient species far longer than mainland environments. In this view, islands are not merely isolated spaces, but slow-moving ecological systems where evolutionary and environmental processes unfold at reduced pace. There are also broader questions about perception of extinction itself. Extinction is often treated as a single event, but in reality it may be better understood as a process distributed unevenly across space and time. Some populations vanish quickly, while others persist in diminishing fragments for millennia. The mammoths of Wrangel Island represent one of the final chapters in that process. But even this narrative may be incomplete. Sea level changes following the end of the Ice Age submerged vast coastal regions around the world. If other isolated mammoth populations existed on now submerged landmasses, their traces may be inaccessible to modern archaeology. In this sense, Wrangel Island may not represent the last refuge of mammoths, but only the last known one, and so uncertainty remains embedded in the record. Why did these isolated populations survive for so long when their continental counterparts had already vanished? Was it purely a matter of geographic isolation, or did subtle environmental and biological factors combine in ways we still do not fully understand? And perhaps more fundamentally, how many other species, like the mammoth, may have lingered in isolated corners of a changing world, their final chapters written slowly across landscapes that have since disappeared beneath sea, ice, and time itself. The final mammoths of Wrangel Island vanish into a narrowing thread of time, their extinction marking not only the end of an Ice Age lineage, but another reminder of how fragile survival can be when geography, climate, and isolation converge. From these distant Arctic landscapes, the narrative of human and natural history shifts again, this time away from extinction and toward something far more subtle, embedded not in bones or ecosystems, but in the human face itself. Among the most striking variations in that face is something so visually immediate that it seems almost ordinary today: blue eyes. They are not rare in perception, yet in evolutionary terms, they are relatively recent. In the cold, shifting landscapes of prehistoric Europe, where Ice Age conditions shaped both environment and migration, early human populations carried a wide range of eye colors. Ancient genetic evidence suggests that early Homo sapiens entering Europe tens of thousands of years ago predominantly had brown eyes, as is common among primate species. The emergence of lighter eye pigmentation appears later in the genetic record, arising through a specific mutation that altered how melanin is produced and distributed in the iris. But unlike many traits shaped by gradual variation, blue eyes appear to trace back to a more singular origin point. Genetic studies have identified a mutation near a region associated with eye color regulation, specifically affecting the OCA2 gene and its regulatory elements. This mutation does not eliminate pigmentation entirely, but reduces melanin in the iris in a way that causes light to scatter differently. The result is not blue pigment itself, but an optical effect, light interacting with structure rather than color substance. This subtle distinction is important. Blue eyes are not painted into the body by pigment, but created through physics interacting with biology. And yet the deeper question is not how blue eyes work, but how they spread. Mainstream scientific interpretation suggests that this mutation likely originated in a single individual or small group, possibly in the northwestern regions of the Black Sea area or nearby Eurasian populations, sometime between 10,000 BC and 6,000 BC. From there, it spread through population mixing over thousands of years. The idea that many blue-eyed individuals today may share a distant common ancestor is supported by the relative uniformity of the genetic mutation responsible for this trait. Unlike eye color variations that arise through multiple genetic pathways, the blue eye mutation appears to stem from a single ancestral change rather than repeated independent occurrences. But this introduces a deeper mystery. Why did this mutation persist and spread rather than disappear through natural selection? In evolutionary terms, traits that do not provide a clear survival advantage often remain rare or fade over time. Yet blue eyes became relatively widespread in certain populations, particularly in parts of Europe. This suggests that factors beyond basic survival may have influenced their persistence. One mainstream hypothesis involves sexual selection. In this framework, traits that are perceived as visually distinctive or desirable may become more common over generations due to mate preference rather than environmental necessity. If early human communities found lighter eye coloration notable or attractive, individuals carrying the mutation may have had higher reproductive success, gradually increasing its frequency within populations. However, sexual selection alone does not fully explain the regional patterns of blue eye distribution. Another factor may lie in population bottlenecks during the post-Ice Age period. As human groups migrated, fragmented, and reformed across changing landscapes, genetic diversity in certain regions may have narrowed significantly. In such conditions, traits present in small founder populations can become disproportionately amplified in later generations. This process may help explain why blue eyes are more common in certain geographic regions today, while remaining rare globally. Yet even these explanations leave questions unresolved. Because the mutation itself is biologically neutral in terms of survival advantage. It does not enhance vision in low light, nor does it appear to provide a clear adaptive benefit in cold or warm environments. And yet it persists with remarkable consistency in the genetic record. This raises a subtle but persistent question. Why does a visually striking trait with no clear functional advantage become so integrated into certain human populations? Some researchers suggest that the answer may lie not in biology alone, but in perception. Human beings are highly sensitive to facial variation, particularly in the eyes. Eyes are central to social interaction, communication, and emotional recognition. A small change in eye appearance can significantly alter perception of identity or expression. In this context, blue eyes may have carried social or symbolic significance in early human groups, influencing interaction patterns in ways that are difficult to reconstruct from archaeological evidence alone. But beyond established theories, more speculative interpretations occasionally appear in broader discussions of human evolution. Some propose that aesthetic traits like eye color may have played a larger role in early social structuring than currently understood, potentially influencing group identity or cohesion in subtle ways. Others suggest that the rapid emergence of blue eyes within a relatively narrow genetic window raises questions about how quickly certain traits can spread through small, interconnected populations. These ideas remain outside mainstream consensus, but they highlight the complexity of interpreting traits that are both biological and deeply perceptual. Because unlike skeletal features or metabolic adaptations, eye color is not just a physical characteristic, it is also an experience shared between observer and observed. It exists at the intersection of genetics and perception, biology and meaning. Ancient DNA recovered from skeletal remains in Europe confirms that blue eye-associated genetic markers were present in individuals living thousands of years ago, but not uniformly distributed. This suggests that the trait emerged during a period of significant demographic and environmental change, when human populations were shifting, mixing, and adapting across post-glacial landscapes. In such a context, even small genetic variations could become amplified through migration patterns and social structures that are only partially visible in the archaeological record. Yet, one of the most intriguing aspects of blue eyes is their relative uniformity across distant populations today. Despite appearing in different regions, the underlying genetic mechanism remains closely linked, suggesting a shared origin rather than multiple independent developments. This convergence points toward a single, relatively recent evolutionary event that left a lasting imprint on human diversity. And still, questions remain. Why did this specific mutation arise at that moment in human history? Was it purely chance, emerging in a population undergoing rapid change? Or did environmental and social conditions create a context in which such a trait could persist and spread more effectively than in earlier periods? And perhaps more quietly, what does it mean that something as subtle as light scattering in the human eye could become a lasting marker of deep ancestry, connecting millions of people across time to a single, ancient genetic variation? As we move from Ice Age extinctions to human migration, from consciousness to perception itself, the origin of blue eyes becomes part of a broader pattern. A reminder that evolution does not only shape survival, but also appearance, perception, and the ways humans recognize one another across generations. And so the question lingers, quiet but unresolved. How many other human traits, so familiar today that they seem timeless, are actually the result of rare, fragile events buried deep in our shared genetic past? Events that could easily have unfolded differently, leaving an entirely different reflection staring back from the human face? The genetic trace of blue eyes lingers like a quiet signature in the human story, subtle, recent, yet widely dispersed across populations shaped by migration, isolation, and time. It is one more reminder that human traits often emerge from narrow windows of history, carried forward by chance as much as necessity. And as attention shifts from inherited appearance to the lived span of human life itself, another question arises, even more intimate and elusive. Why do humans age and die the way they do? And why does human longevity vary so dramatically across individuals, populations, and eras? The question begins not in laboratories or statistical charts, but in the silent contrast between human lives. In ancient burial grounds scattered across Eurasia, Africa, and the Americas, skeletal remains reveal patterns of mortality that differ sharply from modern expectations. Many individuals appear to have died in early adulthood or middle age, while only a small proportion reached what we would now consider advanced age. Yet even in prehistoric contexts, there are occasional signs of long-lived individuals. Bones showing healed fractures, extensive wear, and prolonged survival through injury and hardship. These fragments suggest that exceptional longevity is not new. It has always existed, but unevenly distributed. In modern times, human lifespan has increased dramatically, particularly over the last few centuries. Advances in sanitation, medicine, nutrition, and public health have extended average life expectancy in many regions from roughly 30 to 40 years in pre-industrial societies to over 70 or more today in some parts of the world. Yet this statistical improvement masks a deeper biological question. What sets the fundamental limits of human life? Mainstream biology frames aging as a complex interplay of cellular damage, genetic programming, and environmental influence. At the cellular level, DNA replication accumulates errors over time. Telomeres, the protective caps at the ends of chromosomes, shorten with each cell division. Mitochondrial function declines. Protein structures become less efficient. Over time, these microscopic changes manifest as aging at the organismal level. But even this detailed explanation does not fully answer the broader question of why aging exists in the form it does. Because from an evolutionary perspective, natural selection tends to prioritize traits that enhance reproductive success, not long-term survival. Once an organism has reproduced, the selective pressure to maintain perfect biological repair diminishes. In this framework, aging is not a designed process, but a byproduct of evolutionary trade-offs. Yet this explanation, while widely accepted, leaves room for deeper inquiry. Why does the rate of aging vary so significantly between individuals, even within the same environment? Why do some populations show higher incidences of extreme longevity? And why do certain individuals appear to age more slowly, maintaining physiological function far beyond statistical expectations? In regions known for unusually high concentrations of centenarians, such as Okinawa in Japan, Sardinia in the Mediterranean, or parts of the Caucasus Mountains, longevity is not only a matter of genetics, but also environment and lifestyle. Diets rich in plant-based foods, low chronic stress levels, strong social cohesion, and consistent physical activity are often cited as contributing factors. These observations suggest that longevity is not governed by a single mechanism, but by a network of interacting influences. Still, even in these regions, extreme longevity remains rare. Reaching 100 years of age is exceptional. Reaching 110 or beyond is rarer still. And beyond that threshold, verified human lifespan records become increasingly uncertain, entering the realm where biology and record-keeping intersect with statistical anomaly. This raises a subtle but persistent question. If human lifespan is biologically constrained, why does the upper boundary vary at all? Some researchers suggest that human longevity is influenced by evolutionary history stretching far beyond Homo sapiens. As mammals, humans inherit biological systems shaped by millions of years of evolution, where survival beyond reproductive age provided diminishing evolutionary advantage. This may have set a broad upper limit on lifespan, even as environmental improvements extend average longevity within that boundary. But not all variation can be explained through evolutionary constraint alone. Epigenetics, the study of how gene expression changes without altering DNA sequences, adds another layer of complexity. Environmental factors such as diet, stress, exposure to toxins, and social conditions can influence how genes are activated or suppressed over time. This means that biological aging is not entirely fixed, but responsive to lived experience. In this view, longevity becomes less like a predetermined clock and more like a dynamic system shaped continuously by internal and external conditions. Yet even this model does not fully capture the extremes observed in human lifespan variation. There are documented cases of individuals living far beyond 110 years, though such cases are extremely rare and often subject to verification challenges. These individuals challenge assumptions about fixed biological limits, raising questions about whether aging itself may be more flexible than traditionally understood. Some experimental research explores the possibility that aging could be slowed, paused, or partially reversed at the cellular level through mechanisms such as stem cell regeneration, senescent cell removal, and genetic reprogramming. While these studies remain in early stages, They suggest that the biological processes underlying aging may not be entirely irreversible. But even if aging can be influenced, the deeper mystery remains intact. Why does consciousness persist through time in the form of aging experience at all? Because longevity is not only a biological phenomenon, it is also a subjective one. Humans do not simply age, they experience aging. Memory accumulates, identity shifts, perception of time changes. A year in early childhood feels different from a year in later life. Time itself appears to accelerate subjectively as years accumulate. This raises another dimension of the mystery, the relationship between biological time and experienced time. Neuroscience suggests that perception of time is linked to memory formation and neural processing speed. As these systems change with age, subjective experience of time also shifts. But this explanation describes correlation, not essence. Why consciousness should experience time at all remains an open question, closely tied to earlier explorations of awareness itself. Across cultures and history, longevity has often carried symbolic meaning beyond biology. Ancient texts frequently associate long life with wisdom, virtue, or spiritual alignment. While these interpretations are not scientific explanations, they reflect a long-standing human fascination with extending the boundaries of existence. In archaeological contexts, evidence of care for elderly individuals in some prehistoric societies suggests that long-lived members may have held social roles beyond physical labor, perhaps as knowledge keepers or cultural anchors. This implies that longevity may have had social value in addition to biological persistence. Yet the uneven distribution of lifespan across history and geography remains striking. Why do some individuals age rapidly while others maintain health into advanced years? Why does the biological clock appear flexible in some contexts and rigid in others? And to what extent is lifespan shaped by factors that are still not fully understood or measurable? Beyond mainstream science, speculative ideas occasionally emerge. Some propose that aging may not be a single process, but a convergence of multiple biological systems that degrade at different rates. Others suggest that longevity could be influenced by yet undiscovered regulatory mechanisms within the body that respond to environmental complexity in ways not fully mapped by current biology. There are also broader philosophical interpretations. Some frameworks view aging not as a failure of the body, but as an emergent property of systems designed for change rather than permanence. In this view, mortality is not an accident of biology, but an integral feature of dynamic life systems. Still, none of these perspectives fully resolve the central question, because even if all mechanisms of aging were understood in detail, the reason why biological systems are structured this way would remain open to interpretation. As we move through the long arc of human history, from genetic traits like eye color to evolutionary adaptations like hair loss to cognitive mysteries like consciousness itself, the question of longevity sits at the intersection of all of them. It is about bodies, time, and experience converging in a single lived trajectory. And so the mystery persists. If human lifespan can vary so widely under different conditions, what does that reveal about the true limits of biological time? Are we observing a fixed boundary, or simply the current expression of a system still not fully understood? And perhaps the most profound question remains suspended beneath all others. If aging is shaped by processes both internal and external, how much of human longevity is determined, and how much remains even now unwritten?